everybody. Welcome in. Welcome in. How's it going? Hope everybody's having a good day today. Just getting started here. So, yeah, sorry about that. I woke up a little bit later than I anticipated. And yeah, here we are. We're going to get started on the CompTIA Network Plus. We're going to be working on Chapter 2 today. Chapter 2. So, let me get everything pulled up here. Getting some coffee brewed in the background. Yeah, this is a good time to get your coffee and then your note-taking implements, if you would. I get everything all pulled up. And we'll get a study guide pulled up. We'll get Cisco Packet Tracer going today. But yeah, how's everybody doing? It's April 6th at 1900. I'm ready for some study. Time to get the nerd on. Yeah, it's been a fantastic week. We're on the weekend now, so no complaints. Gotta love it. Oh, I did forget to grab a coffee cup, so I might be doing that here in a second. Can't forget the coffee. So we got the Cisco Packet Tracer. Then I need my note-taking implement. Yeah, let me go grab that real quick. I'll be right back. One sec. All right, we're back. We're back. Sorry about that. But yeah, we're just getting set up here. I have my little duffel bag I take with me everywhere. Actually got this in Thailand. So pretty nice. It's nifty. Just going. And it's where I'll keep my Remarkable Paper Pro. Taking notes as we go along as well. Because remember, I'm also a student. I'm not an expert. So this is actually helping me. I get to go back and refresh stuff that we learned about earlier in class. Oh, yeah. And it's super easy to hook this thing up to the computer. That way I can share my notes with you guys as well. Back to the Wi-Fi. And share the screen. Get us a pad to work on. Perfect. That. Get things organized on our desk. So let's see. Have anybody watching right now? Nope, not yet. All good though. All good though. We'll work through it. So if anybody joins in, we're gonna be going slow and steady through chapter 2. We're gonna get through as much as we can today. And if we need to make a part 2, we'll make a part 2. Because the last live stream was like 5 hours long. That's a bit much because I also have to study for this week's material as well. And yeah, we're in chapter 15. We have to read chapters 15, 16, and 17, I believe it is. Yeah. Let's see. I don't know if we'll need Cisco Packet Tracer all too much in this week. So this week we're going to be going over the OSI model. which is just a model that kind of breaks down the different layers of how we can get information from one device to another device. So, yeah, the Open Systems Interconnection Specifications. That's what that is. And we'll go through it slow and steady. This is something that I hear is tested on the CompTIA Network Plus test if you go to take that certification. So we'll definitely just break it down nice and slow. Anyways, yes, I hope everybody's doing good. Let's get started on this. And I don't know if anybody's seen any of the shorts or not. I'm using Opus Clip for that. Let me double check, make sure I'm giving that name correctly. Yeah, Opus Clip. So yeah, let me know for sure if that seems like it's garbage or not. Because I've looked at some of them and I've gotten some negative feedback in some of the comments and then some dislikes. So let me know if those are horrible. Because the one thing that I don't like about Opus Clip is it makes me look like I'm an expert and I know what I'm talking about when I'm really not, as you guys all know. Yeah, I mean that's the whole premise of the channel, right? Is I'm learning with you guys. So some stuff I'm a little bit more familiar with since I did that coursework a few weeks ago, but it's still fresh to me. So we'll get through it. We'll get through it. All right. Hopefully you have your pen and paper. You're ready to take some notes. We're gonna go through it. We're gonna get started nice and slow. Unless anybody has any questions that they want to work through right now. And I'll try my best to keep an eye on the comments. If anybody does have a question that they want answered or something we can research together. Because, yeah, I love learning. I love learning, and this is the perfect time for us to stop and take a look-see at, different cyber and tech-related questions. And I definitely think that's a mindset to have when we're getting into cyber is you should be hungry for knowledge at all times and wanting to learn. As long as you have that mindset, you'll succeed. And never doubt yourself. Never think like tech is too much for me. I by all means am just a caveman, if you would. I had no exposure to IT or tech, and started with just self-study for quite a bit, and then college finally started breaking into the core components of IT just with this class right now that I'm taking. And we're in week 6 of that. So 2 more weeks of CompTIA Network Plus. All right. Take a look. All right, well, let's just bust right into it. So I'm ready. Are you ready? Get to it. So I have the CompTIA Network Plus study guide open for chapter 2. Again, I don't know too much about copyright, so I'm not going to constantly show the study guide and read through it exactly line by line because I need to make my own original content and avoid that. I'm sure CompTIA would get a little upset if I took their paid for study material and was just giving that to you guys for free. But by all means, we can absolutely go through the information bit by bit. So, the OSI, the Open Systems Interconnection. Let's switch that over to my desktop view. That way you guys can see. At least you guys can see the notes. And making sure my audio is coming through good. Perfect. So OSI. Open Systems Interconnection. So you'll hear quite a bit about the OSI model being a layered model, and it's not like with these layers that everything is so separated that they have no correlation to one another. It just tries to break it down into a concept that with each of these layers, as long as we have protocols and things happening that are in place at these layers on a consistent basis, systems that don't match each other can still communicate. For example, if you have an iPhone and I have a Samsung phone, I can still get on WhatsApp or Facebook Messenger and send you a message. This model is just created so different types of operating systems can talk to each other. And there's 7 layers to it. So it depends on how you want to write it. But all the labels are exactly the same, like layer 1 through layer 7. So layer 1 is always the physical layer. All right. Layer 2. Oh, can't write today. Is the data link layer. Layer 3 is the network layer. And if you guys hear any noise in the background, I apologize. That's my coffee pot going. Layer 4 is the transport layer. Layer 5 is the session layer. Layer 6 is the presentation. And lastly is layer 7 is the application layer. And we can just get rid of the word layer. That's redundant. All right. And we'll cover each of these things individually, but just starting off, these are our 7 layers, and you can just write them in order like this if you'd like. Layer 1 is the physical, layer 2 is the data link, layer 3 is the network, layer 4 is transport, layer 5 is session, layer 6 presentation, layer 7 application. And if you have started your Coursera Google IT Support Fundamentals classes, you'll be exposed to this as well. And this is pretty important stuff to cover. And let's just follow along with the study guide before I start rambling too much about it. Because the study guide does go in depth into it. And it's going to keep us a little bit more structured. So you're going to see me pause quite a bit here and there, and then we'll talk about something as it relates to the study guide and its level of importance. So yeah, right off the bat, they go introducing the 7 layers there, the OSI model, Open Systems Interconnection model. Then we're going to go into data encapsulation and decapsulation within the OSI model. And then we're going to explain common ports and protocols, their applications, and encrypted alternatives, being connectionless versus connection-oriented. So that right there, so our connection less versus connection-oriented. So connection-less is going to be our UDP, which is our user datagram protocol. And then our connection-oriented our connection-based protocol is going to be TCP IP, which is our transportation control protocol. Let me look through, make sure I don't make a fool of myself. Give me the right answer. All right, give me a second. Transmission control protocol, there we go. And then IP is internet protocol. All right. So let's just go ahead and for now we'll minimize Cisco Packet Tracer, and then as we need it, we'll pull it up. I don't think we'll need it for now, but we can also go and let me get the Google pulled up and get us a nice, pretty little figure. I like pictures. So let's see, OSI 7-layer model. Get us a nice, beautiful picture pulled up. I don't think I'll get in trouble for having a picture. There we go. So we'll open image in new tab. There we go. And we can get that there. We'll grab you. Perfect. That's not the most good looking image. It's kind of blurry. Let's get a better one. We can do better. Open image in new tab. Why are you so hard to find? There you are. There we go. Ah, that'll work. That'll work. So, let's get back over to our study guide before I start rambling ahead, because we'll have it nice and structured. All right, if we're going with the study guide, we're getting ourselves prepped up for the exam. So it is a hierarchical system. Just as a refresher of what we're talking about here. So the bottom layer, the layer 1, the physical layer, is the way in which data is transmitted through physical media. So that's going to be our fiber, our Ethernet, our Wi-Fi. the way our friends talk, all the way up to the application. You can think about the application as in my Facebook Messenger, my email, um, every application that we're actually working with, and all the stuff in between is the way in which that information gets there. So it may look really confusing, and you can rewrite it to where everything is restructured to where like this is at the top, and then we work our way down to having application all the way down to physical being at the bottom. So application here, and then physical being down here, if that makes it easier. Because the way it's going to work is we have the application layer at the top. The application, presentation, and session are kind of meshed together all in one basic thing, because that's all about making sure that the application is working and we're getting all of our data ready to go down to those lower layers to be transported out and then go back to the other layers on the receiving end's device, right? So it kind of works all the way down, and then on the receiving end, it works itself all the way back up from the bottom up. All right. Yeah, so it's hierarchical. Let's see. And then we're going to work on encapsulation later. So internet networking models. So they go on to talk about the very first networks that were created by DECnet solutions or an IBM solution, but not together in the 1970s. The OSI, Open Systems Interconnection, reference model was created by the International Organization for Standardization to help different types of computers going on. Because historically, we had like IBM that was making their own computers. Everybody was getting in back in the day. Everybody was getting into making computers, but nobody had a way of talking to each other because they were completely different operating systems. So like IBM computers could talk to themselves. And I'm trying to remember off the top of my head, like the different computer manufacturers back then. But yeah, it seemed like back then in the 70s, we had DECnet and then IBM, and they couldn't talk, and that was becoming an issue. But I mean, it was still kind of neat because, like, if you were like a college or DoD was actually really working, Department of Defense was really working on computers, and like their computers could talk to each other, and some colleges had computers that could talk to each other, but there was no way to really have those computers talk to other computers out there. So they created the OSI model in order to kind of set a foundation in place, because it helps to get other computers to talk. It really helps with troubleshooting when we have connectivity issues, all of that good stuff. So that's why the internetworking models started coming up. So there's the OSI 7-layer approach, and then when I was going through Coursera, they had like a 5-layer approach to it as well. But for the CompTIA Network Plus, they definitely stick to the OSI 7-layer approach. And if I recall, a little bit later on, we're going to go into the way DoD had things set up, which was kind of like a different layered approach there. So yeah, he goes on to explain that the reference models are a conceptual blueprint of how communication should take place. Yeah, when communication is designed in this layered approach, it's a layered architecture. Yeah, and then he goes on to give an example of, say you and some friends want to start a company. First thing you do is sit down and think through the tasks that need to be done. and then who's going to do them and what order you're going to do them. Ultimately, you need to make the correct departments for your company. Like you need to have a customer service department, an inventory department, shipping department, and everything has their own unique tasks in order to make a business function properly, right? And that's one of the big things with the OSI 7-layer approach to it is each layer has its own specific thing that it's in charge of doing. It's all working together ultimately to get information from one device to another device. Let's see. Then he explains that he's going through and he's going to be using the departments for a business as a metaphor for the communication system, explaining how things run smoothly and the staff in each department has to trust and rely on heavily on others to do their job and completely handle their unique responsibilities. Yeah. Okay. We can get past his analogy real quick. So they go on and break through the advantages of having a reference model. So we have a short list of benefits to using a reference model, which is the open systems interconnection model divides network communication processes into smaller and simpler components. It helps in developing, designing, and troubleshooting new systems, right? It allows for multiple vendor development through the standardization of network components. So, yeah, like I was mentioning earlier, the lady has an iPhone, I have a Samsung, and we want to be able to, text each other. And if we both have WhatsApp or Facebook Messenger or Instagram, things of that nature, we want to be able to talk to one another. If we didn't have like an OSI or a hierarchical layered model in place so we could talk to each other, we might not be able to because we have different operating systems. Let's see. It encourages industry standardization by defining the specific functions that occur at each layer of the model. Allows various types of network hardware and software to communicate. It prevents changes in one layer from affecting other layers, facilitating development and making application programming much easier. So, one of the greatest functions, we're getting into the next part now. One of the greatest functions of the OSI specification is to assist in data transfer between disparate hosts, regardless of whether they're Unix, Linux, Windows, or Mac OS based. Let's see. Yeah, he does go on to explain that the OSI model isn't a physical model, it's conceptual and comprehensive, yet fluid set of guidelines which application developers utilize to create and implement applications that run on a network. It also provides a framework for creating and implementing networking standards, devices, and internetworking schemes. All right, and he goes on to drop down and explain once again the 7 different layers. So I have it written out to where physical is layer 1 and then application is layer 7. You can write it the other way, as I explained just a second ago, with having the application on the top. And that's actually a better way of writing it out too, because if we think about it, if we have my phone right here, right? And I have on my phone, let's make a more rectangular phone. So I have my phone. This is Thomas's phone. And I want to talk to somebody. We're going to go through the 7 layers. So we're going to go through 7, which is application. Let me make some room on my desk here. And then we have presentation. Session. And transport, right? Yep, transport. Then network. Then data link. And then physical. And then once all of this information has been put together, because we get information from the application layer, the presentation layer, the session layer, then once it gets to the transport layer, it's encapsulated. Same thing with the network layer, it's encapsulated. Same thing with the data link layer, it's encapsulated again. And then it gets down to the physical layer where it's turned into ones, 0, 1, 0, 1, 0, 1, 0. It goes through some form of physical media or transmission media, which is like my cell phone service. It's my Ethernet cable. It's my Wi-Fi. It's any form of that physical media that where it's turned into ones and zeros. And then we're going to go into somebody else's 7-layer model. So this is the receiving phone. We'll draw a better phone. So this is the receiving phone. And it's going to go into their 1, physical, 2, data link, 3, network, 4, transport, 5, session, 6, presentation, and then 7, application. All right. So that's in essence how it goes. So starts at the application, works its way down the OSI model, all the way until we get to the physical media, the physical way in which that information travels as ones and zeros, as electricity, as photons of light going across fiber, or as a radio frequency going across my cell service, or whatever you may have. It goes through that physical media, and then it works its way back up the OSI model once it gets to the receiving end. All right, and then they provide like a little image that I'll show you guys in the study guide here. It goes from the application layer all the way down to the physical layer, and they have some nice color coding. And you can see that they've kind of grouped some stuff together, right? We can see that we have the application, presentation, and session layer that are kind of grouped together. Transport and network are kind of grouped together. And then data link and physical are kind of grouped together. Okay. Let's start working our way down. And let's just read through what it has here in the study guide. So at the application layer, we have our file, print, messages, database, and application services. At the presentation layer, we have data encryption, compression, and translation services. At the session layer, we have dialogue control, and we'll go into detail on this in a little bit, so don't be overwhelmed and stressed out. It's okay. And I can leave this up for just a little bit longer so you guys can take notes. Here, let's do that real quick. I'll just leave that image up. We'll get a nice little snip of that. I'll leave that up for a bit. I don't think I'll get copyright for just having that. I'll leave this up so that way you guys can reference it real quick. Nothing to stress out too much about. Can I zoom in on you? Yes, I can. All right. So then we have the session layer, which is our dialog control. Transport layer is going to be our end-to-end connection. Network layer is routing. Routers are layer 3 devices. Data link layer, which is framing. That'll be our switches. Switches are layer 2 devices. They're really smart. They look at the, if we remember from the first video, switches look at the MAC addresses, which are the hardware addresses. Routers look at IP addresses, which are our logical addresses. And then from data link, it gets turned into our ones and zeros, and it says physical topology, which is our transportation media. That's our Ethernet cables. That's all of the wiring and stuff that we have set up. And hubs, I believe, are technically part of the physical layer because they don't do any like assessment on the frames themselves. Okay. So I'll leave that up for a bit as we're working through the study guide in case you wanted to take notes on that. So it says the OSI's 7 layers are divided into 2 groups. The top 3 layers define the rules of how applications working within host machines communicate with each other as well as with end users. The bottom 4 layers define how the actual data is transmitted from end to end. Okay, we'll go ahead and make a summary of that here. And then we're going to have, it was the first 3, correct? Yep, the first 3. And we'll write that out over here. So we have 7, 6, and 5, which is application, presentation, and session. The first 3. And those define the rules of how applications working within host machines communicate with each other as well as with end users. So it defines the rules of how applications working within host machines communicate with each other. So defines how applications between host machines communicate as well as end users. And then we'll go 4, 3, 2, 1, which is transport, network, data link, and physical. So our bottom 4, let's see what it says here, define how the actual data is transmitted from end to end. So defines how data is transmitted from end to end. All right, and hopefully my handwriting is neat enough for everybody to use. And by all means, please, if you want me to try an alternative method of note taking for you guys, like let me know. because I can go in here and add text and type things out if need be. That way it's a little bit neater. But my methodology for learning is definitely always handwritten notes. All right. And then we have the figure that we showed. So we have a different little table that they provide as well, where they kind of break down the layers in a little bit more detail than this right here. So let's see if we can't get that moved over. So we'll go new, and then I'll try to grab this all up. Actually, real quick, let's cancel that. Sweet. Grab our snip tool, new. Perfect. And let's make this a little bit bigger. We'll zoom in. So the application layer is going to provide a user interface. So where's my phone at? I don't know where I put it. There it is. So for example, let's see. What's a good application that nobody can steal my PII from? So how do I want to do this? All right. I think we'll go, yeah, this is fine. This will work. So I'm part of a thing in college called NSLS, which is National Society of Leadership or something with college. But if we can think of the application layer, I have an app, right? And this is just an app in my phone. Well, when I want to go and send data to the server on the app, we still have to go through the whole entire 7-layer approach, right? So this being the application itself, but when I go to like send data to the server, we work through the presentation, the session, in regards to setting that up through the app when I go to send it. And then after I've made a request to send data to the server, it goes through the transport network, data link, and physical layer as well. All right. So the application provides a user interface. Presentation presents data, handles processes such as encryption. The session layer keeps different applications' data separate. So a good one for the session layer is, imagine you're researching a college paper. And I can demonstrate this here. Let's see. Yeah. So Google search a few things real quick. Bunnies. Yeah, I'll just bring up my web browser here. That way you guys can see, right? So I have my YouTube page pulled up here. I have the images on the OSI 7-layer model here, and then I have images of bunnies pulled up. Well, the session layer is going to be responsible for keeping that data separate. All right. We don't want to mix data from Google searching bunnies here with the OSI 7-layer model images with my CompTIA Network Plus Chapter 2 YouTube video. We don't want that data being smashed together and causing a gigantic problem. So the session layer is going to be in charge of separating these things out. And then going to the transport layer provides reliable or unreliable delivery. That's going to be our TCP/IP or UDP, which we'll get into in a bit. The network layer provides logical addressing, which routers used for path determination. Data link layer combines packets into bytes and bytes in the frames. Provides access to media using MAC addresses and performs error detection, not correction. And then the physical layer moves bits between devices, specifies voltage, wire speed, and pinout of cables. All right. Get back over here. And then as he says, looking at the figure, it's clear that the actual user interacts with the computer at the application layer. So the application layer is what we're interacting with. It's our user interface. It's our Google search bar. It's our WhatsApp. It's our Facebook Messenger. And then remember, none of the upper layers know anything about networking or network addresses. So the application layer doesn't know jack about like your MAC address. It doesn't know anything about your IP address. All right. So the application layer. And we'll go through and we'll read a little bit of it and we'll talk about it. So the application layer of the OSI model marks a spot where users actually communicate or interact with the computer. So technically, users communicate with the network stack through the application process, interfaces, or application programs interface. So it gives us an acronym there, which is API. And I really need to get better at making notes. So let's do this. We'll do sticky notes if it works today. And those are just YouTube videos I had with music for background music. So let's do this. We'll do API, which is the, I lost my spot. Application Programming Interfaces. So APIs, Application Programming Interfaces. I got Microsoft Word. That's better than sticky notes. Word. Yeah, because I can make things bigger. Let's go with that. Who doesn't like Microsoft Word? Let's shrink that down just a little bit. It's a little bit too large. All right. We'll use this Word document here for our acronyms. So we have API, then we have OSI, which is our Open Systems Interconnection. And did we have any others? Yep, we do. We have UDP, which is User Datagram Protocol. Then we have TCP IP. We'll just break that down into its own things. TCP is Transmission Control Protocol. Yep. And then IP is going to be our Internet Protocol. Perfect. All right. And we'll just minimize this for now. And you guys can let me know if you want me to pull that back up or if I need to keep it up for a little bit longer. I'll leave that up to you guys. You guys run the channel too. And where did OBS go? There we go. All right. So hopefully you've had some time to take notes on this. We'll go ahead. Yeah, I'll just keep this up for now. We'll move our way down here. All right. So users communicate with the network stack through application processes, interfaces, or application programming interfaces, APIs, that connect the application in use to the operating system of the computer. The application layer chooses and determines the availability of communicating partners, along with the resources necessary to make the required connections. So the application layer chooses and determines the availability of communicating partners, along with the resources necessary to make the required connection. That's something worth noting. The application layer is going to ensure that the other user is available, and it's going to determine the resources necessary to make the connection. So it'll be like, oh, I need X amount of bandwidth, so on and so forth, before you get like your session expired and things of that nature. It coordinates partnering applications and forms a consensus on procedures for controlling data integrity and error recovery. The application layer comes into play only when it's apparent that access to the network will be needed soon. So I can still open up like Facebook Messenger, even though I'm not connected to the internet, and it will determine, if I'm not connected to the internet, that we're going to have an issue because the resources necessary aren't there. So the application layer comes into play only when it's apparent that access to the network will be needed soon. Take the case of Chrome or Firefox. You can uninstall every trace of networking components from a system, such as TCP/IP, the network card, and so on. And you could still use Chrome to view the local HTML document without a problem. So the HTML document is just when I first load the website, right? So when I go in, and let's find my internet. Where's my internet? Get back here. Bunnies. When I go and I click Google, this page right here, this page is an HTML document. So when I load this, that's what it's talking about. All right. Oh, that's my spot. So yeah, you can still use Chrome to view the local HTML document without a problem. But things would definitely get messy if you tried to do something like view an HTML document that had to be retrieved using HTTP, which let's not stress out about these acronyms too much right now. Yeah, to view the HTML document that had to be retrieved using HTTP, or nab a file with FTP, which is File Transfer Protocol, or TFTP, because Chrome or Firefox responds to requests like those by attempting to access the application layer. So the application layer acts as an interface between the application program, which isn't part of the layered structure, and the next layer down by providing ways for the application to send information down through the protocol stack. So browsers don't reside in the application layer. It interfaces with the application layer protocols when it needs to deal with remote resources. So the application layer is also responsible for identifying and establishing the availability of the intended communication partner and determining whether sufficient resources for the requested communication exist. The tasks are important because computer applications sometimes require more than just desktop resources. Often they unite communicating components from more than one network application. An example would be file transfers and emails, enabling remote access, network management activities, and client-server processes like printing and information location. Many network applications provide services for communication over enterprise networks, but for present and future internetworking, the need is fast developing to reach beyond the limitations of the current physical network. So yeah, the application layer, if we were to just do a quick summary, the application layer is what we interact with. And at the same time, the application layer is going to determine the resources we need. So let's do that real quick. We'll go application. And so for application, it is, let me get my mic situated. What we interact with. And it determines, I cannot write today. What resources we need. So it's what we interact with, and it determines what resources we need. So moving on to the next part, the presentation layer. And it's not, the presentation layer isn't too long. Same thing with the session layer. So if we look back to our little table here, we see that it presents data and it handles processing such as encryption. All right, before we take a deep dive into that, it's coffee time for me. All right. So it doesn't look like we have any comments, no questions yet, right? No questions. Here's a good spot to pause if we have any questions about what we covered so far. So let's go back in. Let's pop quiz. Pop quiz. We're going to minimize this and minimize this and minimize this real quick. So actually, I didn't need to do that. I can just make myself big. Yeah, I'm just a normal human. I'm not a YouTube personality. But I do like teaching. It's something I enjoy a little bit. I'll get these things back to normal on my computer. So what does OSI stand for? What does OSI stand for? I'll give you guys a countdown while I'm setting things back up. I just destroyed it. All right, OSI is the Open Systems Interconnection. What is layer 7 of the OSI model? That would be the application layer. Perfect, perfect. Layer 5. Do we have our notes? Layer 5. Layer 5 would be the session. Perfect. Layer 2 is data link. Layer 1 is physical. What is physical? What is the physical layer? What does that talk about? What does the physical layer? What's the idea of the physical layer? Physical layer is our actual physical media. It's our Ethernet cables and the ones and zeros that go through them, right? Perfect, perfect, outstanding. And then I mentioned it earlier. Do we remember where a router exists in the 7-layer OSI model? What layer does a router exist at? That would be level 3, the network layer, because it looks at the IP addresses. And the layer 2 looks at what? The MAC address, that burned in address, that hardware address. All right, good job, good job. All right, I got some coffee now. Hopefully you do too. I'm going to take just a quick 30-second, 1-minute break. Text the lady real quick. Hopefully you don't mind. I'll be right back in just a second, okay? right, and we're back. We're back. Sorry. Can't have everybody hearing me like use my silly voice. Okay, where'd we leave off? We were just about to get started on the presentation layer, right? Yes. So let's get our notes pulled back up. Go back over to our desktop capture. All right, here we go. Do we need this anymore? I think we should all be good, at least have a good understanding of where things are in here with this little note. So we'll go ahead and get rid of you. And then we'll pull our Word document up. That's where we're keeping all of our acronyms. So we have API, which is the Application Programming Interfaces, OSI, which is our Open Systems Interconnection. And then we have UDP, which is User Datagram Protocol. And then TCP, which is Transmission Control Protocol. IP, which is Internet Protocol. All right, so let's go through this. The presentation layer gets its name from its purpose. It presents data to the application layer and is responsible for data translation and code formatting. A successful data transfer technique is to adapt the data into a standard format before transmission. Computers are configured to receive this generically formatted data and then convert it back into its native format for reading. For example, from EBCDIC to ASCII2. We'll look at that in just a second, but let's continue on. By providing translation services, the presentation layer ensures the data transferred from one's system's application layer can be read and understood by the application layer on another system. The OSI has protocol standards that define how standard data should be formatted. Tasks like data compression, decompression, encryption, and decryption are all associated with this layer. Some presentation layer standards are even involved in multimedia operations. So let's go back a little bit. So we saw something that seemed kind of interesting to me. It said computers are configured to receive this generically formatted data, then convert it back to its original native format for reading. For example, EBCDIC. Where I'm at right now in the CompTIA Network Plus, I've not really seen anything that really breaks down what EBCDIC is. So let's take a look at that real quick, just because I'm kind of curious and I think learning things is awesome. That's why we're here. And make some room real quick. So we'll go and look at EBCDIC. So Extended Binary Code Decimal Interchange Code. It's an 8-bit character encoding system developed by IBM, primarily used for legacy IBM mainframes to represent text and control characters. It encodes 256 unique characters, 0 to 255, using 8 bits, often for banking and large-scale legacy or mission-critical industrial applications, while it provides reliable performance on specialized hardware. Major disadvantages include its lack of portability with standard ASCII Unicode systems and incompatibility with modern web standards. So it sounds like EBCDIC is an older legacy model of ASCII. So ASCII, I forget what the acronym stands for. ASCII is essentially speaking a way of representing all of our different characters, like ABC, 1, 2, 3, the money sign, the division sign, all of our different characters on the internet through character encryption, which I kind of covered on before. So it seems like the presentation layer, what it's going to be doing is going to take information and do a conversion, right? It's going to take the machine code, it seems like, which is like our software engineers and like what they do. And it's going to convert stuff from that into something that is usable and readable for us. So it's presenting information to the application layer. That's a primary function of the presentation layer. So I guess if we were to oversimplify it, if we were to try to take, what's the word they use? If we're trying to abstract it, right? If we're trying to take a complex idea and oversimplify it, we can just break it down into the presentation layer is in charge of encryption and ensuring that information is presented appropriately to the application layer. So let's go ahead and get that into our note. Because when I first went through doing this coverage on my own before I started really making any YouTube content on it, I was like, oh, wow. And I, more or less speaking, wrote word for word everything in the study guide to try to memorize it. But I don't think that's necessary per se. So the presentation layer presents data to the application layer. All right. And then as we saw with our snip that we had, which I got rid of, another thing that the presentation layer does is it's in charge of decryption, encryption, things like that. Let's see, go back to the study guide and find that for sure. Oh, and there was also a note before the presentation layer. Let's go through that. So note, it's important to remember that the application layer acts as an interface between application programs. For example, Microsoft Word doesn't reside at the application layer. It interfaces with the application layer protocols. So he goes on to explain in chapter 6, we'll have an introduction to Internet Protocol, and we'll talk about the key programs or processes that actually do reside at the application layer, like file transfer protocol, and then TFTP, which I think is like trusted file transmission protocol. Yeah, we'll see. We'll see as we get there. Because one of the rough things was like sometimes with college, they like to throw the reading material out of whack. So week 1 was covering chapter 1, chapter 2, and then chapter 6. So as we get later into it, it's like, I forget everything about chapter 6, which was a pretty important thing because that covered your TCP IP. I wasn't ready for it. All right. So refreshing presentation layer. So presentation layer presents information to the application layer. Application layer is what we interact with. So presentation layer presents, application layer is what we interact with, if we're just trying to make it simplified. And the presentation layer provides translation services. All right. And then the presentation layer handles tasks like data compression, decompression, encryption, decryption. All right. So with encryption and decryption, I think that one's a little bit easier to explain. we can look into compression and decompression and see what that actually means here in a sec. We'll check that out. But yeah, if you use like Signal or WhatsApp, I don't know if Facebook Messenger has encryption off the top of my head, but I do know like Signal and WhatsApp encrypt data. And all that essentially does is it scrambles the data around, so that way if somebody was just looking at it, you can't like easily part and piece that information together to see what was actually sent. So encryption is the process in which we scramble the data, and then the receiving end has to have a key. It has to know how to reassemble the data. And that's what decryption is. It's reassembling that data in the proper order, the proper way, so that way it's readable. So the presentation layer handles that. Let's check out what data compression is. We have the internet and we're working through it together. We're going nice and slow. So let's see. Let's get those caps locks off. What is data compression? So let's make this nice and big for us so we can read it. Zoom in a little bit. So here's what it says with the AI overview. Let's see if this makes sense. Data compression is the process of reducing the size of data files to save storage space and speed up transmission by encoding information using fewer bits. It optimizes digital storage and bandwidth for allowing for faster data transfer and reduced storage infrastructure needs. So types of data compression. We have lossless compression, and this isn't tested on the CompTIA Network Plus. This is just us being nerds, okay? Let's just be nerds together. Let's do it together. So types of data compression is lossless compression, reduces file size without losing any information, allowing for perfect reconstruction of the original data. It is essential for text files, spreadsheets, and program files where losing data is not acceptable. Lossy compression. Sounds like the inverse of that. So reduces file size by permanently eliminating non-essential information, particularly data that is less perceptible to human senses. This is commonly used in audio, MP3, images, JPG, and video, MP4, to significantly reduce file size. So key concepts and techniques, algorithms. Algorithms such as run length encoding identify repeating patterns and substitute them with smaller codes. Other methods include dictionary-based coding. Sometimes I can read. I apologize. Codecs. Used to compress and decompress data, often for streaming services or in storage systems. Performance optimization used in databases, for example, PostgreSQL, Toast, and data lakes to improve query performance and lower storage costs. So yeah, it looks like just overall, we have lossless compression, which is the ability to reduce the file size without losing any data, and lossy compression, which is like we can lose some stuff and still not suffer too much from it. All right, so we have an idea of what data compression is now. I think it's useful for us to look through things together. All right, refreshing the move. So presentation layer presents data to the application layer. Application layer is what we interact with. Presentation layer presents that data. So it's in charge of encryption, decryption, compression, decompression. All right. Next up, session layer. And yeah, we can get there. The session layer is responsible for setting up, managing, then tearing down sessions between presentation layer entities. This layer also provides dialogue control between devices or nodes. It coordinates communication between systems and serves to organize their communication by offering 3 different modes: one direction, simplex; both directions, but only one direction at a time, half duplex; and bidirectional, full duplex. He says to sum up, the session layer keeps an application's data separate from one application's data. So an example he provides is having multiple web browsers. All right, let's do this. Let's try to explain this. Oh, I'm feeling much better after having coffee. Let's go with this. So let's check it out, right? Let's check it out. Let's get the Googles up. Yes. So let's see, is anybody watching? Let me bother people. I don't have my YouTube channel pulled up. We can do that. We can do that. Boom. YouTube over here. We'll take a gander. All right, no one's watching. That's okay. Let's take a look at it. So we have this Google page here, right? And let's see. We're going to go Google something else here. We're going to Google something here. So let's look up bunnies. All right. So I'm interacting with the application layer. And then when I hit enter, what's going to happen here is we're just talking about the session layer right now. There's a lot of other stuff that's taking place. So when I hit enter, we're going to establish a session with Google servers, because Google's our search engine. And Google servers, so it's going to be like, hi Google server, or you're going to be like, what's up? Bunnies. I got you. And then we're going to get bunnies. So that's the session layer. We're going to establish a connection. We're like, hey Google. And they're going to be, what's up? I see that you said something. And I'm going to be like, bunnies. And they're going to be like, okay. So we're going to establish the session. And then when I get bunnies, after I say, hey Google, when I press enter, that's when it starts. When I press enter, it's hey Google. And they're going to be, what's up? And we've established, essentially speaking, connection there. It's a little bit more. There's called the 3-way handshake, which is we're going to try to synchronize, and they're going to be like, oh, I got you. Let's synchronize. And I'll be like, okay. So that's a 3-way handshake. We're going to set up a session. They're going to provide us data, and then they're going to tear down the session, because it's not constantly talking back and forth. Because when I press enter right now, I get this. And after I get bunnies on my screen, we don't have to talk anymore, because I got bunnies already. We don't need to keep talking. So that's the end of it. It tears down the session. We set up the session, we got bunnies, and then it tore down the session. We don't need to keep talking. And we got bunnies. And then if we go over here and we look at, let's see, cats. Same thing. We set up a session, we got cats, it tears down the session. As far as I understand, that's a good way to explain the session. So I interacted with the application layer, and I asked for bunnies through the session layer. Well, and then the presentation layer presented me the information to my application, and then it showed me all of the stuff. So essentially speaking, that's what we have here. We established a session with Google. Cats or bunnies came from the session layer with Google that we set up, received it at the presentation layer to the application layer, which I can go and interact with. I can click on cats. I can interact with this. So the presentation layer decrypts, uncompresses, all that good stuff, presents that information to my application. That's a good way of doing it. Hopefully I did all right at explaining that. Yeah. All right. Let's get rid of our cats and our bunnies. And we can minimize you for now. Get this back up. All right, so that covers the session layer. Session layer is responsible for managing, setting up, and tearing down sessions between presentation layer entities. All right. It's also in charge of dialogue control between devices or nodes. Nodes is just another word for devices. Like my computer's a node, my laptop's a node, my cell phone's a node. It's just a networking device. All right, let's go and talk about the other thing that they brought up here, which I think is very important to cover, which is simplex, half duplex, and full duplex. All right, let's see. Let's see here. I can destroy things. I have a short video where I destroyed an Ethernet cable, which I think is super useful, at least as far as understanding the concept of simplex, half duplex, full duplex. And let's see. I think I can draw a picture. Or should I destroy things? Let's see. Let me go grab an Ethernet cable real quick, and I'll be right back, because science. All right. 1 second. I will be right back, and I'll destroy an Ethernet cable for you guys. I just remembered it's still in my trash can. Victory. All right. Let's see. So this is an Ethernet cable, right? This is what plugs into our computers. I don't like where. Come here, you. All right. So check it out. This is going to be harder. We don't need to go over all the details of an Ethernet cable right now. But if you can see these twisted pairs in here, right? See how they're all twisted together? So let's just look at one set of cables. So when we're talking about simplex, that means communication only goes one way. Only goes one way. Meaning I only talk to you. That's it. Or you only talk to me. There's never a switch back and forth. Never, never. It's only I talk to you, or only you talk to me, or only I talk to whatever other device. Only that. There's never a switch back and forth. That is simplex. It's one way communication. Only from me to a device. Only from a device to me. Only. So, half duplex, which you still need 2 wires for with simplex or half duplex. You still need the 2 wires. 2 wires are needed for one-way communication. And the reason is because one's going to be positive and then the other is going to be kind of a ground. And it just helps when we're switching back and forth with the voltages, having a positive wire, then having a negative wire, helps us with modulating those back and forth quicker and quicker between positive and negative. Because essentially speaking, what happens is our computers, when we're trying to talk to each other with our ones and zeros, with our voltages, they're going to come up with an agreement. They're going to be like, okay, let's synchronize our clocks. So that way we know how much data is going to be going for X amount of time. So let's just say how many bits per second are going to happen. And based on synchronizing the clocks and then having an understanding of I'm expecting this much data in this much time, when the voltage is positive and negative back and forth, it can understand how much data is being transferred and what that data actually is. But you still need the two wires. So simplex is only in one direction. It's a one-way street. And then we can think about, so yeah, here's a good way of thinking about it. So imagine you're driving in a city. Simplex is literally just a one-way street. Cars can only go one way. And then for a half duplex, it can go one way at a time. So imagine you're on a 2-lane road, and we'll come up with a picture here. I like drawing pictures. I'm a visual learner. This helps you out. So let's go back to my desktop. So for half duplex, imagine we have our street, right? So for half duplex, we have construction workers here, and we need to keep them safe. So exactly like this lane is blocked, so nobody can go here. And we have the guy standing here with a stop sign. That's a really bad stop sign. I'm sorry. And then we have the guy here with our stop sign. No. You know, stop signs are going to be circles today. And we can think about it as cars can only go this way for a second. And then after the cars are done going that way, then the cars can go this way. Okay? Cars can only go one direction at a time. That's half duplex. Let me just delete that real quick. I love this thing so much. Best learning tool I've ever gotten. So let's go back to my camera. Only big camera. I'm sorry. Nobody wants to see it. All right. So we have one of our sets of wires, right? And so I can talk to you, but you can't talk to me for a while because we don't want that collision. And then after I'm done talking, then you can talk to me. So that would be half duplex. Simplex is I can only talk to you. Our one-way road. Simplex is our one-way road. Half duplex is we have construction and traffic can only go one way at a time. So it can only go this way. And then when traffic's done going this way, then traffic can come this way. So that is our half duplex. Full duplex involves two wires. That way, we have our 2-lane road. Traffic can be received and sent at the same time. You need at least 2 wires. So traffic can be received and sent at the same time. That's very important to remember. It's important to remember simplex versus half duplex, full duplex. I think I covered that one pretty good with my analogy of traffic. So let's refresh it. What is simplex? Simplex is one direction only, one-way street. Half duplex is one direction at a time. Direction. Full duplex can send and receive data at the same time. Send and at the same time. And we want full duplex. Full duplex is always superior. We want to be able to send and receive at the same time. Okay. We were at the session layer. So session layer, refresh that. Session layer. We'll go back to my desk. I'll throw this back away. All right, let's go back to the desktop. Let's have a sip of coffee. All right. So the session layer is responsible for setting up, managing, then tearing down sessions between presentation layer entities. Also provides dialogue control between devices or nodes. It coordinates communication between systems and serves to organize their communication by offering our three different modes: one-way street, simplex; construction, half duplex, one direction at a time; full duplex, we can send and receive data simultaneously. So he adds, to sum up, the session layer basically keeps an applications layer data separate from other applications data. So we went on to explain what the session layer looks like with our search of, where are you at? With just having Google here, and then we can have Google here. We have our different things. We have cats, and then we have bunnies. I can spell today, I promise. So we have cats and bunnies. That information's not getting all smashed together and turned into some awful cat bunny compression hybrid. All right. It keeps everything nice and separate. It establishes the session. And then we have our three different modes of communication, which are simplex, half duplex, full duplex. Simplex being only one direction, half duplex being one direction at a time. Full duplex is we can send and receive data at the same time. Okay, so session layer. Let's make our note. So session creates, destroys, and manages sessions between presentation layer entities. Keeps data separate. And then last are modes of simplex, half duplex, and then full duplex. Oh, I am sorry. My cats are in the way. All right. And I think that's worth keeping in our little note over here. So let's go with that. We'll go with simplex. Only one direction. Go away. Of communication. And then we have half duplex, which is one direction at a time, but can send, then send and receive. And then we have full duplex, which is can send and receive at the same time. All right, I think that's worth keeping in our little note over here. I know it's not an acronym, but it's important enough to keep over there. Okay, next, if we need a little break, go ahead and take a little break now. All right, we're just going through it bit by bit. We're not trying to information cram. We're going through it bit by bit. Where are we at right now in the time? An hour and 42. I am sorry. Next is the transport layer. So a lot of stuff happens at the transport layer. I need to top up my nicotine. 1 second. A lot of stuff happens at the transport layer. And it gets a little bit more complicated, but that's okay. That's why we're here. We're going to go through it slow and steady. Because I'm also learning at the same time, and I love the fact that I get to refresh this knowledge with you. So the transport layer. The transport layer segments and reassembles data into a data stream. Segments and reassembles data into a data stream. Services located in the transport layer handle data from upper layer applications and unite it onto the same data stream. They provide end-to-end data transport services and can establish a logical connection between the sending host and destination host on an internetwork. The transport layer is responsible for providing the mechanisms for multiplexing upper layer applications, establishing virtual connections, and tearing down virtual circuits. So here we're getting into our three-way handshake, okay? We'll get to that in a sec, I think. It also hides the many sundry details of any network-dependent information from the higher layers, facilitating data transfer. And then it says we'll cover TCP and UDP thoroughly in Chapter 6. So, yeah, that is its own game when we get into TCP and UDP. TCP is Transmission Control Protocol. UDP is User Datagram Protocol. Right here, we'll pause right here. So let's just briefly give you guys some insight on TCP and UDP, and we'll go to making me. So TCP, Transmission Control Protocol, is reliable transportation. So essentially speaking, we have our data, and in essence, it's reliable transportation because when we send a little bit of data to the receiving party, we're going to send a certain amount of data. And then we are expecting after a certain amount, which we agree upon. We agree on, hey, I'm going to send you this much data, and then you have to tell me that you got it. All right. That's what TCP does. It's going to be like, hey, I'm going to send you this much data, then you have to tell me you got it. So let's go. And then after you get that much data, you tell me like, hey boss, I got that data. I'm like, cool. And then I'll send you some more. And then that's how it'll go. It's reliable in the sense that I, as the sender, am expecting that you will acknowledge that you've received the data. So it's kind of like certified mail, if you would. You're signing off that you received it, and then you get the little notification as the sender like, hey, they got it. So it's kind of like certified mail in that it's reliable. All right. UDP is unreliable in that I can just constantly send you data. So it works perfect for what I'm doing right now, which is streaming. UDP is great for streaming because if there was the constant sending YouTube data and then needing acknowledgments back and forth, that's just going to take more time. And that's not good. Whereas I can just keep throwing data at YouTube with UDP, and that's way better. It's way better that way. And same thing if you're watching if you're watching Game of Thrones on HBO, I think it is, right? If you're watching Game of Thrones, you don't need your TV to constantly tell Amazon, because I think that's where right, Amazon Prime, watch HBO through there. You don't need your TV to constantly tell Amazon like, hey boss, I got that video footage. Just letting you know. You don't need that. It's just going to take more time, and it's not necessary. So that's just a brief summary of TCP and UDP, which they break down a lot of the details in later bits. But yeah, let's keep going. Let's keep going. All right. So he explains that we'll cover TCP and UDP thoroughly in Chapter 6, which we will. TCP is reliable, UDP is not. The two protocols give application developers more options because they have a choice between them when working with TCP IP protocols, which is Transportation Control Protocol, Internet Protocol. And then he has a note. The term reliable networking relates to the transport layer and means that acknowledgements, sequencing, and flow controls will be used, which we'll cover. We'll cover in Chapter 6 thoroughly. But we know now that TCP is reliable. We need acknowledgements. UDP is not. We can just keep tossing data. All right. So the transport layer can be connectionless or connection-oriented, but it's especially important to really understand that connection-oriented portion of the transport layer. So we'll take some time to cover that. So connection-oriented communication. So before a transmitting host starts to send segments down the model, the sender's TCP, Transportation Control Protocol, process contacts the destination's TCP, Transportation Control Protocol, process to establish a communication. The resulting thing is known as a virtual circuit. Virtual circuit. This type of communication is connection-oriented. So we'll write that down real quick, okay? We're in the transport layer right now. So we have transport. So we have the transport layer. And in the transport layer, let's give me some more room. Transport. So we have connection oriented and connectionless. All right. So connection oriented. And we'll write it in here. Connection oriented. So connection oriented. So before a transmitting host starts to send segments down the model, the sender's TCP process contacts the destination TCP process to establish a connection. And we have a virtual circuit. So we have a virtual circuit, and that is connection oriented. During the initial handshake, that's what they call it, a handshake, the two TCP processes, TCP is Transportation Control Protocol, processes also agree on the amount of information that will be sent in either direction before the respective recipient's TCP sends back an acknowledgement. So yeah, we just talked about that. Hey, I sound like I know stuff. Yeah. With everything agreed on in advance, the path is paved for reliable communication to take place. Cool. I'm actually kind of proud of myself. That's nice. And then we have a figure. And we're going to go into the three-way handshake. Okay? Here we go. Let's do it. Let's test my drawing ability. Are we ready? So we have our virtual circuit. Here's what that looks like. So we have our computer. And then we have, so this is ours. And then we have our receiver. And then we have the three-way handshake. We're gonna talk to each other to set up a virtual circuit. So what I'm going to do as the sender, right? I'm the sender. This is my computer. I'm going to synchronize with my receiver. I'm going to send a SYN. And then they're going to send a SYN, a synchronize, ACK, acknowledgement, back to me. And then after I get their synchronize back and then their acknowledgement, I am going to send back to them an ACK. And we'll put that over here. So we have SYN, which is synchronize. I can't spell. I'm sorry. Ah, there's an H in there. And then we have ACK, which is which is acknowledge. So we have a synchronize acknowledgement, and then acknowledge. Then after that, the connection is established. We have created a virtual circuit. And then we're going to start sending data so the data transfer can happen. So we have our three-way handshake. All right. So we can see this, right? We have our computer, we have the receiving computer. To set up a virtual circuit, we're going to send a SYN, then they're going to send back to us a SYN ACK, and then we're going to send an ACK. The connection is established, data transfer can begin. All right. So it goes on to explain in the illustration I basically showed for you. It's the same thing. Depicts a typical reliable session taking place between sending and receiving systems. Both of the host's application programs begin by notifying their individual operating systems that a connection is about to be initiated. We have the three-way handshake that takes place here. The two operating systems communicate by sending messages over the network, confirming that the transfer is approved and both sides are ready for it to take place. After all of this required synchronization takes place, a connection is fully established and data transfer can begin. So the virtual circuit setup is called overhead. Overhead. And we'll set that over here. Overhead is, let's find that again. The establishment of a virtual circuit. Let me make this bigger for you guys. We can do that. There we go. That way it's easier to read. So overhead is the establishment of a virtual circuit. Okay. While the information is being transferred between hosts, the two machines periodically check in with each other, communicating through protocol software to ensure that all is going well and that data is being received properly. So remember, this is our connection-oriented setup with the transport layer. Connection-oriented. With the connection-oriented, we're going to be sending a certain amount of data before we need them to tell us that they received it. And if something bad happens, we'll cover that a little bit later. But essentially speaking, we're going to be sending them data, and then after we've reached the end of our agreed upon data amount, they're going to tell us either acknowledged, or they're going to be like, hey, we're missing this. And then we're going to send that, and they're going to be like, hey, we're good now. And then we'll start sending data more. Okay, that's our connection-oriented TCP process. So we can sum up the steps with, first, we have a connection agreement, which is the request for synchronization. So first is our request for synchronization. So let's go ahead and write that down. Our steps. Our steps for connection. So first is a request for synchronization. All right, that's the first thing we sent. The next segment, acknowledge the request and establish connection parameters, the rules between hosts. The segments request that the receiver's sending is synchronized here as well, so that a bidirectional connection is formed. Bidirectional just means a two-way connection is formed. So the next segments acknowledge the request and establish the connection parameters. So that would be when we're sending back that SYN ACK, remember? So step 2. So step 2 is acknowledge. Well, it's going to be a SYN ACK. So the SYN ACK is going to set up the connection parameters. So connection parameters. And remember, with our connection parameters, that's going to be the agreed upon amount of data to transfer before we need an acknowledgement back. So we're setting that up. The segment requests that the receiver's sending is synchronized here as well. So that's part of the SYN ACK as well, so that a bidirectional connection is formed. And then our third step, so connection parameters, we have our clocks that are synchronized, and then agreed on, how do I want to word that? Agreed on amount of data before an ACK, which is acknowledge, is required. All right. So we're synchronizing our clocks, we're agreeing on the amount of data before an acknowledgement is required. We're setting up the rules. And so here we can just set up rules. And then our third step is the final section. The final segment is also an acknowledgement and notifies the destination host that the connection agreement has been accepted and that connection has been established. Data transfer can now begin. So that's our final acknowledgement. And connection is agreed upon. Data transfer. Ooh, I cannot type today or write today. can begin. All right. So here's what we got, right? We have our three-way handshake, and we can just call this step 1, step 2, and then step 3. So step 1 is we have that initial, hey, let's go ahead and synchronize because I want to send you stuff. Then step 2 is that synchronize acknowledgement, which is I agree to set up a connection with you. Here's the rules. We're defining the rules. And then step 3 is that final acknowledgement of I agree to the rules. Data transfer can begin. All right. So he goes on to explain that sounds pretty simple, but things don't always flow so well. Actually, no, let's go back up and read the note. Okay, so they always provide little notes in here. I'll show you. Little notes between the sections. He says he knows that he went into a lot of detail for the setup. So that way we can have a clear picture, but you can refer to this entire process as a three-way handshake. It's known as a synac, ack, or synchronize, acknowledgement, Synchronize, acknowledgement. There we go. So the synac, ack, or the synchronize, acknowledgement. So it sounds pretty simple, but things don't always flow so well. Sometimes congestion can occur during a transfer because a high-speed computer is generating data traffic faster than the network can handle transferring it. And a lot of computers simultaneously sending datagrams through a single gateway or destination can clog things up. A gateway or destination can become congested even though no single source caused the problems. Either way, the problem is like a freeway bottleneck. Too much traffic for too small a capacity. It's not usually one car that's the problem. It's when there are just too many cars that's on a particular route. So the next part we're leading into is flow controls. And we're still in the transport layer. We're still in layer 4, the transport layer. All right. So I'll pause real quick, see if we have any questions. Let's see. Looks like it's just me right now still. So, yes. Another good time for a coffee break. Perfect. So flow controls. Let me actually double check, make sure the stream is going good. Looks like the stream's nice and healthy. No issues. Everything's nice and clear. I don't have moderators working with me, so I do all this by myself. All right, everything's looking good. Okay, so we're going into flow controls. Data integrity is ensured at the transport layer by maintaining flow controls and by allowing users to request reliable data transport between systems. Flow control provides a mean for the receiver to govern the amount of data sent by the sender. It prevents a sending host on one side of the connection from overflowing the buffers in the receiving host, an event that can result in lost data. Reliable data transport employs a connection-oriented communication session between systems, and the protocols involved ensure that the following will be achieved. 1. The segments delivered are acknowledged back to the sender upon their reception. Any segment, number 2, any segment not acknowledged are retransmitted. Number 3, segments are sequenced back into their proper order upon arrival at their destination. And number 4, A manageable data flow is maintained in order to avoid congestion, overloading, and data loss. So in essence, go back to me, and then maybe we draw some pictures. So in essence, what flow controls are doing is, if you can imagine that I have my cup and I have my coffee pot. Dangerous. So I have my cup and I have my coffee pot. There is a reasonable amount of coffee I can pour into the coffee cup at once. And we want a reasonable amount of coffee to be flowed into my cup at once. Now, if I were to take a pressure washer to try to fill up my coffee cup, and you can envision this, right? Super high pressure water, a lot of volume of water spraying into my cup, and then the cup is just flinging coffee and water all over the place. That would not be good. We want a reliable, consistent amount of coffee to go into our cup at once. The other problem is if we have too much data coming in, our computer has memory, cache, that it's collecting the data and holding it so it makes sure that everything is lined up in the correct order so it can move it up, right? If we send too much data at once, we run out of memory at cache, and then we have an issue because now we can't assemble everything in an orderly fashion. And if we don't have the memory, we can't store it. So that's what flow controls do, is it prevents us from overflowing the buffer. That buffer, all that really means is we have a certain amount of data we can hold on to until we can reassemble it. If we have too much data there, then we lose whatever's being sent after that. So that's what flow controls do. It helps the segments deliver and acknowledge back to the sender upon the reception. Any segment not acknowledged are then retransmitted. Segments are sequenced back in their proper order upon arrival at their destination. A manageable data flow is maintained in order to avoid congestion, overloading, and data loss. So let me see. I can make a visual example. Right? Oh, do I have a pen? I don't need a pen. Or do I? So let's imagine that I have a pen. Okay. I'm going to go along with this visual. All right. So this is going to be a data segment. And there's a few things on this. We of course have a bunch of data, right? We have all of the data. We have who is sending the data, who's receiving the data, and then we have a sequence, right? So this is like my page number. Imagine I had a really big document and you're numbering your pages. So imagine I have now a bunch of these. This is exactly what it's like when you're working with a computer. You have a bunch of these. So you can imagine that if I start sending a whole bunch of these faster than you can process them, and I'm just throwing them on your desk, you can get to a point to where your desk is too full to keep it organized and stuff falls off the desk. That's exactly what it's like when we're sending data. So imagine the desk. The desk is the receiving computer's buffer. It's their cache, their memory. They're able to hold on to stuff. And when I have to put these on their desks, I'm trying to, as best as I can, put them on the desk in order. So we have page 1, page 2, page 3, page 4. And on each of these, I have who it's from, which is me, who it's going to, some other information, and then sequencing number. The sequence numbers, if you can think of it, are exactly like the page number. So if I put a bunch of these things on your desks, you're looking at it, and then we're making sure that we're putting it all in order. Page 1, then page 2, page 3, page 4. And so what we're talking about with flow controls here, and what we're talking about with the transport layer here, is that when I put a bunch of papers on your desk, if we're missing something or if something falls off the desks when you're trying to reassemble these, you tell me like, hey, Thomas, I'm missing page 5,620. I'm like, oh, okay. Then I resend page 5,621. But we have sequence numbers in place here. And the flow controls that we're talking about are if I start throwing too much paper on your desk, stuff's going to fall off. And then that's when you, the receiving machine, tell me like, hey, stop. I have to work on this real quick. I'm like, oh, okay. And then you say, okay, I'm good now after you finish processing it. Or if something's missing, you're like, hey, I'm missing page 5,621. I'm like, okay, here's page 5,621. You're like, good to go. And then I start sending you more pages. That's what we're talking about with flow control. I'm a visual learner, so hopefully that analogy helps. All right, so once again, let's refresh the move. We have, on the transport layer, established a virtual circuit with our three-way handshake. All right, we have our request for synchronization. We have synchronizing and then acknowledgement coming back to us. We're making the rules. We agree upon the rules here, which is how many pieces of paper I can give you before I require you to tell me that you received them. And we synchronize our clocks, all that good stuff. And then we have the last acknowledgement that goes out to you. We've established our virtual circuit. Our connection is established. And then data transfer can begin. Those are our 3 steps. And our flow controls are our agreed upon terms, right? That we agreed on in the second step, which is like, hey, send this amount of data before you require an acknowledgement. And then we have rules in place to where if I've sent you too much data at once, we can pause, then I can start sending data again. And then in addition to that, if you're missing something, you tell me, hey, I'm missing this, and then we can proceed to retransmit it, and then tell me, all right, we're good. We can keep going. Okay. So what happens when a machine receives a flood of datagrams too quickly for it to process? It stores them in a memory section called a buffer. But this buffer tactic can only solve the problem if the datagrams are part of a small burst. If not, and the datagram deluge continues, a device's memory will eventually be exhausted. Its flood capacity will be exceeded, and it will react by discarding any additional datagrams that arrived, like a dam spilling over. So as I use the analogy of like coffee spraying all over the place or papers falling off the desk, we have an issue if you get too much data. If I filled up your whole desk, things are going to start falling off. So it sounds pretty bad. And we go on to explain what happens next, which is I'm sending, and then the receiving device is like, hey, buffer full, not ready, stop. Might take you a little bit of time to work through everything on your desk. And then you're like, hey, all this is processed, go. And then I'll send, and I'll send, and I'll send, and I'll send again. So let's get back to the desktop capture. And here's the figure that they show when they're explaining this. So we're sending, we're sending, we're sending. And then if it's too much, if I start to exceed your memory cache there, you're like, buffer full, not ready, stop. Segments processed. After you've had some time to sort through everything, go. And then I'll start sending and sending and sending again. All right. Which we're halfway done. Good job, everybody. We're halfway done. All right. So on to the next part. So he goes on to explain that it's similar to a stoplight. All right. Signaling the sending device needs to stop transmitting when it's overwhelmed its peer. The peer machine receiver processes the segments abounding in its memory reservoir, its buffer. All right. Which I think that's awesome. Like I never thought about like buffering in that context. Like when you think about like a video game loading, or like if a video is buffering, like we're trying to do is like organize and configure stuff, and it takes a little bit of time to process. Then we need to collect some more information, organize and configure it. All right. Where's our next thing? Then after that, it sends out a ready transport indicator. When the machine waiting to transmit the rest of the datagram receives this go indicator, it resumes the transmission. During fundamental, reliable, connection-oriented data transfer, datagrams are delivered to the receiving host in exactly the same sequence they are transmitted. So, if any data segments are lost, duplicated, or damaged along the way, a failure notice is transmitted. This error is corrected by making sure the receiving host acknowledges it has received each and every data segment and in the correct order. All right. We're almost done with transport. So we're summarizing this. To summarize, a service is connection-oriented if it has the following: a virtual circuit, three-way handshake, SYN, ACK is done. It uses sequencing, like I told you, page 1, 2, 3, 4. They do that with the datagrams. All right. And transport layer is datagrams. Datagrams, transport layer. A virtual circuit is set up. It uses sequencing. It uses acknowledgement. It uses flow control. All right. And we'll go ahead and jot that down real quick. Uses. Oh, let's get rid of that. Three-way handshake. Virtual circuit. Sequencing. Uses acknowledgements. And then lastly, uses flow controls. All right, windowing. We're on to the next one. All right, we're still in the transport layer. Still in the transport layer. So let me pull this back down. And we'll refresh the move. We'll go back from the top. So from the top, we want to establish a connection oriented, reliable transportation, TCP, transmission control protocol, TCP, reliable transmission, connection oriented. We start off with sending a request for synchronization. Step 1. Step 2 is we receive synchronization and acknowledgement, setting the rules for how we're going to share data. Then I tell them that I've acknowledged the rules, connection established, which is a virtual circuit, then data transfer can begin. That's our connection oriented TCP process. So windowing. Time for a sip of coffee. Let's check. Has anybody joined up? And watching? Nope. Just me still? All good. Give me just a second. I'm going to be right back. All right, welcome back. Sorry about that. Oh, it's pretty fun actually going through this. Like I genuinely think so. I'm sorry if I kind of go on tangents here and there. I like taking things nice and slow, making sure we understand as fully as possible. Because like with college, it just feels super rushed sometimes. Like, oh, you have these 3 chapters to read out of order, and then you have all of these assignments to do in addition to that. So it's always rushed, and I'm really enjoying being able to go through this slow and steady with you guys, and hopefully it's useful to you too. And if you're here, thank you so much for being here. Um, just as an aside, if you're new to the channel or if you've subscribed to the channel, I never really want to be YouTube superstar. Genuinely speaking, I just want to help other people, and doing a teach back on stuff helps reinforce things here. I've been using Opus Clip, which is kind of neat for making shorts, but I think it definitely takes my channel out of context. It makes me sound like an expert when I'm not. So, yeah, once again, it's just a reiteration. I am not an expert. I am brand new, going through this on my own. So, yeah, I will make mistakes, and I've seen at least one comment so far and some dislikes as well on some of the clips. But hey, it's what attracts people in here. Like, so if that helps draw somebody in and they enjoy the content, then awesome sauce. Or, yeah, I mean, hopefully it just helps. That's all I care. Like, if I can help some other people or get some, even if feedback is critical, I don't mind at all. That's why I'm here. I'm here to learn with you guys. And that's my goal, is to hopefully get enough people in here to where it's like we can have questions and answers, things to look in together. And who knows, maybe down the line, if I get better at it, I can genuinely help people. So anyway, I digress. Let's go on to the next thing. Don't need to talk about me too much. All right, let's go back over to my desktop capture. Okay, so we're about to get into windowing. We're still in the aspect of the transport layer. We've covered and beat into place our connection-oriented TCP process, essentially speaking. We'll get into a lot more details with TCP later on. So windowing. And I don't remember this too much off the top of my head, so hopefully this refresher will help out. It says, ideally, data throughput happens quickly and effectively. So throughput is just a way of describing data's ability to transmit, right? That's what throughput has happened. So like good throughput is like we have a good amount of data being transmitted. Bad throughput is we don't have enough data being transmitted, or maybe we have a bottleneck or something like that. So ideally, data throughput happens quickly and efficiently. And as you can imagine, it would be slow if the transmitting machine had to wait for an acknowledgement after sending each segment. But because time is available after the sender transmit the data segment and before it finishes processing acknowledgments from the receiving machine, the sender uses the break as an opportunity to transmit more data. The quantity of data segments, measured in bytes, that the transmitting machine is allowed to send without receiving an acknowledgement is represented by something called a window. Windows are used to control the amount of outstanding, unacknowledged data segments. It's important to understand that the size of the window controls how much information is transferred from one end to the other. Although some protocols quantify information by observing the number of packets, TCP/IP, Transmission Control Protocol, Internet Protocol, measures it by counting the number of bytes. And then we have a figure we're going to look at. So, when you've configured a window size of 1, the sending machine waits for an acknowledgement for each data segment it transmits before transmitting another. If you've configured a window size of 3, the sending machine is allowed to transmit 3 data segments before an acknowledgement is received. In reality, the window size actually delimits the amount of bytes that can be sent at a time. Okay, so let's talk about this. Windowing. Go back into my big camera. So I gave the analogy earlier, right? Let me scoot back. That way we can see what I'm doing. And I can have a mic. So windowing is a matter of data segment. Why are you pointing? Don't know why I wanted to point over there. Let's lock the camera in place. There we go. Yeah, it just was like, ooh. Anyway, so windowing is a matter of data segment, data segment, data segment, so on. So windowing is like, how many of these can I give you before you tell me that you've gotten them, right? So in reality, we're not going to send like one data segment and then wait for an acknowledgement. Like, here you go. You get that? Like, it's going to be quite a bit. So windowing is a matter of how many of these can I give you at once before you have to tell me that you got them. That's all windowing does. It's the amount of datagrams that can be sent before an acknowledgement is required. We set that up in step 2 with the SYN-ACK, the synchronized acknowledgement. So in step 2, we set up the windowing. How many of the datagrams can we send before I require you to send me an acknowledgement? All right. So yeah, and then they have a little table for us to look at, which we can check out. So here we have our sending machine, we have our receiving machine. So we agree on a window size of 1. I send 1, you've received 1, and then you tell me that you acknowledged 1. Send datagram number 2, you receive number 2, then you acknowledge number 2. So when we go to larger sizes of windows, I send you 3 windows, right? 3 windows, 3 datagrams. So send 1, send 2, send 3. The way that we get a response back is you acknowledge and then you request the next one, ACK 4, and then you sent 4. Okay? That's how it breaks up. So if I had this sent up to a window size of 156, you'll see send 1 through 156, and then if the receiving machine got all of those,
it'll ACK 157. It'll ACK 157. So it'll be like acknowledged, send 157, send the next thing. All right. Let's go on. Acknowledgements. Acknowledgements. So reliable data delivery ensures the integrity of the data stream being sent from one machine to another through a fully functional data link. Guarantees data won't be duplicated or lost. This is achieved through something called positive acknowledgement with retransmission. Positive acknowledgement with retransmission. A technique that requires a receiving machine to communicate with the transmitting source by sending an acknowledgement message back to the sender when it receives data. The sender documents each segment it sends and waits for this acknowledgement before sending the next segment. When it sends a segment, the transmitting machine starts a timer and retransmits if it expires before an acknowledgement is returned from the receiving end. All right. So let's just summarize all of that real quick. So we have positive acknowledgement with retransmission. So I send you a bunch of stuff, and then once you've received the agreed upon amount within the time that we agree on, then you send me an acknowledgement back, and then I'll start sending some more stuff. If I've sent you a bunch of stuff and you're looking through and processing it all, and maybe you're confused, if a time limit that we agreed on expires, I'm going to be like, I didn't hear from Josh yet on if he got all that stuff. I'm just going to resend it. So we have another figure that we're going to see. The sending machine transmits segments 1, 2, and 3. The receiving machine acknowledges it and requests segment 4. When it receives the acknowledgement, the sender then transmits segments 4, 5, and 6. Here, let's take a look at that. If segment 5 does not make it to the destination, the receiving node acknowledges that event with a request for the segment to be resent. The sending machine will then resend the lost segment. So let's take a look at that. So we sent 1, 2, 3, good to go. Acknowledge 4. Send 4. We tried to send 5. All right, everything looks good to us. We send 4, 5, 6, but the receiver didn't get number 5. Receiver did not get number 5. So it tells us ACK 5. So it wants number 5. Like it's acknowledged the rest, and then it's like, but I want 5. And then the sender sends number 5, and it's like, okay, we're good. And then we go on from there where we stopped. So ACK 7. And then we'll start again. And that's how that goes if something is lost. Or it could be a matter of like we overflowed the buffers, right? We sent 1, 2, 3, and it's like, okay, cool. And then we sent 4, 5, 6, and then maybe the buffers were full for 5. And like it just didn't have the ability to process it. It'll kick back up where it missed, which was sequence number 5, packet 5. Then we'll resubmit packet 5, and then we'll pick back up with where we need to go from there. Perfect. Okay, that's it for the transport layer. So let's summarize what we got here. So working from the top down, all right, we have the application layer, which is the thing that we interact with. We have the presentation layer, which is in charge of encryption, decryption, compression, decompression, and giving info to the application layer. Let's follow along with my notes. There we go. Get that nice and organized. So we have the presentation layer, which presents data to the application. We have the session layer, which creates, destroys, and manages sessions between presentation layer entities. And then we have transport layer, which is where we're working on now. We have the connection-oriented TCP IP. Think about sending and acknowledging like certified mail. And then we have connectionless. Connectionless being our UDP, our user datagram protocol. We don't need acknowledgments. Like you wouldn't need your TV to acknowledge that it received data from your streaming software, from YouTube, for example. YouTube is a great example of this. So if we're going via the route of a connection-oriented virtual circuit, we have our three-way handshake. Step one is a request for synchronization. Step two is a synchronization and acknowledgement, where we agree upon the rules of how we're going to send data. We go for our window size and how much data is being sent overall. And then the last part of that is sending an acknowledgement back. The connection is established. We have a virtual circuit. Data transfer can begin. Okay. Our windows are how many segments we send at a time before we require an acknowledgement. If we were successful in sending our packets, it's going to send us back an acknowledgement with the next packet that we need to send. So if we send 1 through 5 and it got everything all right, good to go, it's going to send back an acknowledgement for 6. If we send 1 through 5 and it didn't get number 5, then it's going to be acknowledge with the missing segment, which is 5. And then we're going to send number 5, and then it's going to send us back an acknowledgement for the next series of windows. And that's the transport layer. We've covered acknowledgements. All right. Yeah. All right. We're almost there. Our next part is the network layer. Network layer. So our next part. Network layer. So for me personally, we're going to take the network layer and probably the data link layer a little bit slower because there's a lot there to cover. So let's just start going through it slowly but surely. Let's just do another quick check, see if anybody's in. Nope, it's just me still. Good to go. If we had questions, we could answer some questions, but we're good. All right. So the network layer. And I don't have a script for this at all, right? Just bear in mind with that. I'm not a YouTube star. I'm just trying to slowly go through this stuff with you guys. So the network layer manages logical device addressing. Logical. What, if we remember correctly, what is a logical address? Our IP addresses, Internet Protocol addresses. Okay. The network layer manages logical device addressing, tracks the location of devices on a network, and determines the best way to move data. This means that the network layer must transport traffic between devices that aren't locally attached. What device is on the network layer? Do you remember? Layer 3 devices. Layer 3. That would be routers. Routers are layer 3 devices that are specified at the network layer and provide the routing services within an inner network. So he goes on to explain that first, when a packet is received on a router interface, the destination IP address is checked. If the packet isn't destined for that particular router, the router looks up the destination network address in the routing table. Once the router chooses an exit interface, the packet is sent to that interface to be framed and sent out on the local network. If the router can't find an entry for the packet's destination network in the routing table, the router drops the packet. All right, there are two types of packets that are used at the network layer. We have data packets and then route update. Data packets and route update. So one thing to show, which I think will be interesting. Let's go back to my big camera. So when we're talking about like a router's exit interface, right? So yeah, let's roll with this. I can't get my... Hey, it's being a good camera. Good camera. Okay. So this is my Omada router switch combo thing. Okay. So this wire here connects to my gateway or my modem, right? Not gateway, disregard gateway. It connects to my modem. My modem goes to my internet service provider. This cable right here goes to my computer. This cable right here goes to my Mac Mini, which I never use. And then this one right here goes out to my laptop in the living room. Okay? So when we're talking about an exit interface, say we had a big corporation, right? A big corporation, and we have a bunch of different networks. And let me draw up an example real quick. We kind of talked about those in my first video. But go back to my desktop capture. So let's just say, for example, we have a building. And we've configured several different networks in our building, right? We have several different networks. And we can just say this is like finance. So this is network 1. We have accounts payable. We have network 2. We have our server room, which will be network 4. We have, let's see, our call center, which is network 3. Like, you guys get the picture, right? And then 5 and 6. So we have different networks. So let's just say I wanted to connect all of these different networks together so that way computers could all talk to each other. Well, I can do that with a router. Okay, so let's just say this is our server room, right? I can spell, I can do it. So this is our server room. Everybody might need access to the server room. Everybody. So, and then we have the ISP, the internet service provider. So say we have somebody from our network here that wants to talk to the server. That'd go to the router, and then from the router, it can go to the server. So we have an interface for network 1, and then we have an interface for the router. So when we're talking about determining an exit interface, it could be on our local area network segment, which is like going from network 1 to our server rooms in network 3. Or it could be from network 5 to network 4. Like James is on his computer in network 5 and he's on Microsoft Teams and he wants to talk to Jimmy in network 4. So it's going to go from our network 5 to our router to network 4. So that's what we're talking about in regards to exit interfaces. Or we have Rebecca on network 6 and she wants to look at cute kitty cat videos on YouTube. So hers would go to the router, and then it would choose the exit interface of the internet service provider to get out to YouTube. So hopefully that kind of gives you guys a little bit of a visual. There we go. Back to nice and clean. So let's go back to what I'm showing here, like a real physical version. And with my router, you can imagine that. I don't have as many ports as like a super big network, but you can see that I have different ports. So imagine that I have this Ethernet cable right here, number 2, which is my computer. This would go to a switch for like network 1. And then this one would go to a switch for like network 2. This one would go to a switch for network 3, so on and so forth. You can imagine like after I get like a big commercial setup here that has a lot more ports, how that becomes important. So if somebody on network 3 wanted to talk to somebody on network 2, the router looks at the IP address from the data packet for network 2 and it'd be like, oh, that's on this port. That's on this port. That's where the network is. It's going to look at the IP address and be like, okay, it's on that port. Let's send it to that exit interface. It's going to have that on the routing table. All right. Let's get my camera fixed. Back here. Yeah. And then we're going to lock that back in so we don't look at the ground. All right. Let's see. So we have all of our acronyms. So data packets. Data packets. There are 2 types of packets that are used at the network layer. Data packets. Actually, let's do a summary real quick. Let's do a summary real quick on the network layer. So network layer, we know, is layer 3. And routers exist here. Routers exist here. Routers exist on layer 3. Layer 3. Okay? So data packet, no, sorry, let's do our summary. So network layer, layer 3. Transports traffic between devices that aren't locally attached. Transports traffic between devices that aren't locally attached. Okay. Actually, we can use Cisco Packet Tracer for this. We can use Cisco Packet Tracer. So let me get over here and open that up for everybody. Actually, yeah, switch back. Let's open that up. So we can set up some networks, right? So we can set up a network. We can have our computers all linked up. We'll call this network 1. So I really want to help visualize this. Where's my note? So we're going to call this network. And then we're going to give it a network ID of 192.168.1.0. Zeros. Not 1.0. I think that'll work. And then we're going to have this 192.168.2.0. Then we're going to have 192.168.3.0. Now bear with me for just a second. 2. 4.0. So you may have seen that in previous examples, I stick to the 192.168. Whatever. And yeah, Those are unassigned IP addresses. So the people who were developing and implementing the internet standards, they created unassigned IP addresses that can never be assigned for stuff like this. Because with IPv4 addresses, we're very limited to how many overall addresses we have. IPv4 is Internet Protocol version 4, which are the 4 octets of 3 numbers. And later on we'll go into like different network classifications and things of that nature. So don't stress about those too much. But we have a group of unassigned addresses that everybody can use. 3 and 5.0. And we're able to use that to get traffic on our local area network or in our office without having to assign everybody their own IP address, and we end up running out of IP addresses for everybody. Because think about how many IP addresses we need. IPv4 is something to the effect of 4-point-something billion total possibilities, which sounds like a lot, but consider the fact that there's over 8 billion people on the earth, and then think about the idea of the fact that your smart TV needs an IP address, your computer needs an IP address, your cell phone needs an IP address. We have smart fridges that need IP addresses. Your cameras need IP addresses. Everything needs an IP address. And we would have ran out of IP addresses so long ago if everything had its own very special, very unique IP address. So that's just a side note, something worth notating. Anyway, so we have network 1. And I know it's a little wonky. You're thinking like, okay, well, network 1 has its IP address of .1.0. What's this thing over here? .2.0. And then we have network 2 that has .3.0. So I can't give you a very definitive explanation on that, but one thing I've noticed is that with setting up routers and ensuring that they can communicate effectively, this is how we need to have them set up for their exit interfaces. So the exit interface is going to have its own essentially like network that links to network 2, because the router here is going to be like, okay, we need to be able to send it to network 2, and network 2 is going to want to send it to network 1, but we have to have something that we can connect together to. And essentially that's what we're going to do. We're going to have a router here. We're going to have a router here. And then we're going to have a router here. All right. And here, let me structure this a little bit better. Actually, I'll bring you guys down a little bit. And then we're going to get a switch. Now, if we remember from the previous video, switches are better than hubs in the sense of they can look at the MAC addresses, the hardware addresses of everything on their interface, everything that's linked up to them. And I know this is going to take a little bit of time, and I apologize for that. And feel free to skip ahead if you want to get past this part. But I think it's good to have, at least in regards to a conceptual understanding of what I'm talking about here. We're setting up our 3 networks. We have different networks. And the point of talking about this is talking about exit interfaces. All right. So we're going to set up, oh, no, we don't want that one. We're going to set up our connection to you. To you. To you. And then to you. And the reason why you want everything linked up to a switch is it's just really good for interconnecting devices. And you don't want a bunch of data going into your router. You want your router to be as streamlined as possible. And this sets us up to where, like, if computer A wants to talk to computer C, it just goes through the switch instead of the router having to figure everything out. And remember, routers use the IP addresses, and we want to reduce all of the overhead on the router as much as possible. And if the router's constantly handling like ARP requests and things of that nature on the network segment, that can cause us some problems later. And we'll cover ARP requests later on. All right. And then, like, you can imagine, like, we could have more computers hooked up here. We could have more switches. Like, we can make like a big beefy network on this first one, just as an example. So like we can hook up another switch here as an example. This will be our big beefy network. Like, networks in their topology are always like super dynamic. Like, there's so much stuff that can change on them. Oops. All right. Okay. So you can imagine this is our network one. And then we're going to set up a serial connection, as I can, between the routers. All right. Routers are going to know that these are our exit interfaces. Okay. So you can see, right? And what we were talking about just a second ago, let's refresh it. I don't think you guys need me to go through and waste the time in linking everything up. You kind of get the idea, right? All of the end devices, which are our computers, are nodes. It could be printers, it could be servers. Like, we can get rid of this. And you guys can imagine, like, maybe we have a server room instead. Maybe we have servers instead. Maybe this is just a gigantic server room that's all connected up to the switch. But when we were talking about just a second ago, refreshing it. So this means that the network layer must transport traffic between devices that aren't locally attached. See how all of these devices here are locally attached, and all of these devices here are locally attached. But like, if this computer wanted to talk to this computer, it's going to have to go through the router. And we could set this up as a different network itself, or we can go back and boom. We could even set it up to be like this. And now all of these devices are, in essence, locally attached, if you would. So, but if this computer, I really need to stop doing that, wants to access data on the server, it's going to have to go through the router. The server's on a different network. Okay? So, this means that network layer must transport traffic between devices that aren't locally attached. Routers are layer 3 devices that are specified at the network layer and provide the routing services within an inner network. It happens like this. First, when a packet is received on the router interface, let me highlight that so I don't lose my spot. Highlight yellow. There we go. So for us right here, right, I can hover on this and it'll tell us the router's interface. Allegedly. Do the thing. You've done it before. Oh, I have to click on it. There we go. So our interface here is FA0-0. That's the interface. We can click on that. configure CLI. Where are you at? I got to remember this real quick. Configure. Here's our interfaces. Interface. So fast Ethernet 00. That's this connection right here. That's that interface. And then we have our serial connection here, router to router. That's going to be one of our interfaces. That's going to be serial 2-0. So if we look at that, serial 2-0 right here, you guys can see. That's what we're talking about, the different interfaces. So when a packet is received on a router interface, that would be this. So say this computer is trying to talk to the servers. When it's received on an interface, the destination IP address is checked. If the packet isn't destined for that particular router, the router looks up the destination network address on the routing table. Once the router chooses an exit interface, the packet is sent to that interface to be framed and sent out on the local network. If the router can't find an entry for the packet's destination network in the routing table, the router drops the packet. All right. So what we're talking about here is, so say computer here wants to access data on the server. So it sends in a request like, hey, I know the information I want on the server. It's going to go into the switch and it's going to go to the router. The router is going to look up in its routing table, hey, what network is the server on? And it's going to be like, oh, it's on network 2. Where do I have to send that? Oh, I have to send that to this address. That's the exit interface, which is serial 2-0. So it's going to get it to serial 2-0. It's going to frame it up. Hey, this is where we're going to next. This is where it's coming from. This is where it's going, with a bunch of other information, and then it's going to send it out. And then the same thing happens here. It's going to receive it on the interface, serial 2-0. And if I linked it up to the switch and stuff like that, it's going to see like, oh, this server is on my network. I know that the exit interface is going to be this Ethernet port. It's going to send it to the switch. The switch is going to look at the MAC address, and then it's going to grab the server. Perfect. So there are two types of packets that are used at the network layer. Data packets. Data packets. These are used to transport user data through the internetwork. Protocols used to support traffic are called routed protocols. Two examples of routed protocols are Internet Protocol and Internet Protocol version 6, which we'll learn about in Chapter 7 for IP addressing. The next type is route updates. These packets are used to update neighboring routers about the networks connected to all routers within an internetwork. Protocols that send route update packets are called routing protocols, and common ones are Routing Information Protocol, which is RIP, RIP, and we'll put that down, and RIP version 2, Enhanced Interior Gateway Routing Protocol, and Open Shortest Path First. Route update packets are used to help build and maintain routing tables on each router. Okay, that may sound like a lot. That's okay. It's okay. We'll get through it. So data packets. Let's go back and refresh that one. Okay. These are, there's the protocols that we use for data packets are routed protocols. And the examples of that are IP, Internet Protocol. So IPv4, IP version 4, which is what we commonly use today. And then the newer version of IPv6. And I know that we cover that in detail later, so we don't need to spend a lot of time talking about that today. But the data packets, the protocols that we use for that are IP. And then IPv6, IPv4. The route update packets, that's okay. That's information we can kind of forego for now because it gets covered heavily later on, which would be RIP, RIPv2, Enhanced Interior Gateway Routing Protocol, and Open Shortest Path First. So the route update. All we have to think about for that is routers talking to each other like, hey, this is where this is. That's it. So the data packets, that's the important thing that we can kind of focus on here. And I think we're done with this example for now. We'll put that away. So data packets. Where's my pen? Uses data packets. I'm going to underline packets. All right. And then protocols used are going to be, we'll do dot. We'll do that. IP, IPv4, IPv6. Okay. And then we're going to do route updates. And that just lets routers learn about other networks. Okay. So layer 3, if we were to just backtrack and summarize it, I think what we have here really emphasizes what we're looking at for layer 3. Transports traffics between devices that aren't locally attached. Looks at IP address. Looks at IP addresses. All right. And it's layer 3. Layer 3 looks at IP addresses. Routers are located on layer 3. Routers are located on layer 3. Transports traffic between devices that aren't locally attached. Looks at IP addresses. It uses data packets. It uses packets. The protocols used are IP, IPv4, IPv6. Okay? The IPv4, IPv6 are just the versions of IP, Internet Protocol. Okay? They're just the versions. Internet Protocol is Internet Protocol. There are different versions of Internet Protocol. So, and the protocols are just the rules. It's the rules for how the data is sent. It tells us like the source IP address, the destination IP address, and it breaks it down into a lot of details. And there are things here that help to get traffic from A to B. It's a lot like when we were looking at my example earlier of this. It's a lot like the idea of making sure we have our sending address, like who we're sending it to, then the receiving address, breaks down the rules, gives us a way to check to make sure everything gets there properly. That's called a header. And we'll cover that in a little bit. I don't think it's in this section at all, but we'll check and see. It tells us and it gives us the rules for how to send this stuff to different networks. Okay? So layer 3 uses routers, looks at IP addresses. We have protocols for IP, Internet Protocol. We have Internet Protocol version 4, Internet Protocol version 6. The other thing that we send out here are route updates. It lets routers learn about their neighbors, other networks, things like that. Okay. And I don't think we need to really work hard on remembering RIP version 2, EIGRP. an open shortest path first. I don't think we need to focus too much on that right now. That's okay. We'll get into it later in detail. Okay, let's go back to our desktop capture. Okay, let's add this to our note here. We have IPv4, which is Internet Protocol version 4, and then IPv6, which is Internet Protocol version 6. Okay. Moving on. Let's see. So in essence, we have a little table here, and it kind of breaks down our networks in a way that we can kind of visualize here, which is what I kind of set up for us. And you can see that we have our different exit interfaces on our router. And these are serial connections. That's just the type of connection that routers have between other routers. So that way routers know, hey, I'm talking to another router here. And we go about our different networks and our different interfaces. All right. Now let's go ahead and get this back to the side, which we kind of already set up. We kind of set up with Cisco Packet Tracer, as you guys kind of saw. It was just a little bit more detailed. Let me find that. All right. We have our network 1. We have the exit interface network. We have network 2. We have the different interfaces on the router that'll go to our switch and to all of our end devices. Okay. Let's move on to the next thing. So it's talking about network addresses. These are protocol-specific network addresses. A router must maintain a routing table for individual routing protocols because each routing protocol keeps track of a network that includes different addressing schemes like IP and IPv6. When it's referencing IP here, I'm more than assuming it's referencing IPv4 because that's what's primarily used, especially when we're talking about inside of our networks. Think of this as a street sign in each of the different languages spoken by the residents who live on a particular street. If there were American, Spanish, and French folks on a street named Cat, the sign would read cat/gato/chat. So yeah, that's what they're talking about with regards to network addressing. They're protocol-specific network addresses. A router must maintain a routing table for individual routing protocols because each routing protocol keeps track of a network that includes different addressing schemes, which would be our IP, IPv6. All right, Internet Protocol version 4, Internet Protocol version 6. And it just gives us a way of signifying, like, if we're using different IP versions, still being able to talk, because you can assign something an IPv4 address and you can assign something an IPv6 address, or you can utilize servers to essentially assign them for you, but that's a different thing we'll get into later. Interface. This is the exit interface a packet will take when destined for a specific network. Okay. Let's go back to Cisco Packet Tracer, cover that again. So when this computer here wants to talk to the server or a computer over here, it's going to route to the router. The router is going to receive it and determine that it's on a different network. After that, it's going to receive it on an interface, and then we're going to have an exit interface. You see that SE2-0? That's the exit interface. It's going to exit there. Then we have the receiving interface, which is the SE serial connection, 2/0 here. And then we're going to probably have an exit interface if we're going to the server of one of our Ethernet ports. So just for funsies, I'll wire that up. And then we'll wire this up just for the sake of demonstration. So we're going to have an exit interface. And that exit interface is going to be the interface 0-0, which we can see here. Fast Ethernet 00. Okay, that's what we're talking about. So we have a receiving interface and then an exit interface. So data goes from the computer up to the router. It receives it on an interface. It's going to look up where that information is going to go, and then it's going to get it to an exit interface to be framed in a way that gets it to the proper network, okay? So then it's going to go boom. Then the router is going to receive it here. It's going to strip some information off of it, figure out where it's supposed to go. Then it's going to do the same thing. It's going to get it to an exit interface, and it's going to send it off. Boom. The switch is going to take a look at the MAC address because it's the hardware address, and then send it to our server. Metric. All right. So we saw that little section of metric, and you may have noticed I didn't talk about it because I kind of forget. So metric. This value equals the distance to the remote network. Different routing protocols use different ways of computing the distance. Oh, yeah, okay. I know what we're talking about now. And we cover that in Chapter 9, Introduction to IP Routing. So for now, just know that some routing protocols, namely RIP, which is Routing Information Protocol, uses something called hop count, the number of routers a packet passes through en route to a remote network. Other routing protocols alternatively use bandwidth, delay of the line, and even something known as tick count, which equals 1/18 of a second to make routing decisions. So metric, just breaking that down into an easy thing. It's just a way for routers to figure out how much work goes into sending something. So for example, with this setup that we have here, let me actually just finish setting this up. That way, I don't know how to click things. I did not do that the way I wanted to. Delete. Let's set this up. I am not perfect. I'm not a perfect teacher. Never claim to be. I just try my best. That's what I'm here for. Okay, I think that's good. So say that I want to send a Microsoft Teams message. So this is me. We're going to do me. So this is me. I'm going to move me over here. Okay? We all see me, right? And then this is John. Okay? Okay, we see John is over here. We're still connected to the switch. So I'm just moving it to where we can definitely see where I am, and then we can definitely see where John is. So the metric we're talking about, if we're talking about hop count, is how many times does my packet go from a router to another router? And with that being said, we typically have a maximum allowed amount of hops. So that way we don't get an instant death loop of maybe something's wrong with how I configured my router, and then we end up getting stuck with it goes from router A to B. B gets confused, thinks it goes back to A, and then we're just having a constant loop back and forth, which is going to eat up a lot of our processing power for our routers. So when we're talking about hop count, the information goes from here to our first router. Our router puts it together, right? And then our router sends it off through our exit interface into the second router. This router takes a look at it, and it's like, okay, this is where it goes. Then it subtracts the hop count by 1. and then it sends it off to the next router. The next router takes a look at it and it's like, okay, I've got this now. I'm going to subtract the hop count by 1, and then it's going to go and process it from there. So you can imagine as we start getting bigger and bigger networks, we're going to be having some more subtraction of hop counts. So the metrics they're talking about is like hop count or any other way that a router measures how it sends data. Okay. So we have hop count, we have delay of the line, and tick count. But we'll get into a lot of those in later chapters in chapter 9. So we don't need to stress on that for now. All right, next. Routers break up broadcast domains, which means that broadcasts by default aren't forwarded through a router. This is a good thing because it reduces traffic on the line. Routers also break up collision domains, but this can be accomplished using a layer 2 data link layer switch as well. Note, broadcast and collision domains will be covered in chapter 5, which we will cover. For now, just remember that routers break up broadcast domains and switches break up collision domains. Because each interface on a router represents a separate network, it must be assigned a unique network identification number, and each host on a network connected to that router must use the same network number. Okay, so with that being said, everything here, if I wanted to give everything here a name, has to have same IP address in essence. So you see how this last octet is 0? That's what I would change dynamically here. And this is its own type of network addressing scheme. Like they have like the A, B, C, D networking schemes, which are covered later. But what I'm talking about here is for this network, we have 192.168.1.0. So if I wanted to assign a name to this guy, let me go through that nice and slow for you guys. So we started off here. This is Cisco Packet Tracer, by the way, which is free, and you can totally buy that yourself. Sorry, buy. It's totally free. You can sign up for it. All it costs is like an email address, and I unsubscribed after that, so I don't get any of the random stuff. But you go into the desktop, IP configuration, and then if I'm assigning it an IP address, it has to have the same core functionality as this. So if I want to assign this computer a number, it could be 192.168.1.1. All right, see how everything matches? And then if I want to assign this guy something, 192.168. I cannot type today. I apologize. 192.168.1.2. See how that last octet is kind of changing? Last octet. 192.168.1.3. So conversely, if we go over here to our network 3, see how it's 192.168.5.0. You can also just write it as 5.x. X can change. But if I wanted to assign this guy something, it would be 192.168.5.1. Okay? And this has its own network, and it falls within the same networking addressing. All right? So all of these would be kind of in line with the same. All of our servers would be, and then all of our machines here would be. We have 192.168.1.0 for this network, .3.0 for this network, .5.0 for this network. So that's what they're talking about there. When he says Each interface in a router represents a separate network. It must be assigned a unique network identification number, and each host on the network connected to that router must have the same. Okay? Let's check real quick, see if anybody's here for any questions. Nope, just me still. All right. Here's some key points about routers that you should commit to memory. Routers by default won't forward any broadcast or multicast packets. So when we're talking about broadcasts, right? Let's kind of demonstrate what I'm talking about. So say this computer wants to learn where this computer is. What this computer is going to do is, if I know this is Billy, I know Billy, but I don't know Billy's address, but I want to find out who Billy is. I send what's called a broadcast address. So what happens from here is the broadcast goes to the switch, and then the switch broadcasts, sends it out to everybody to figure out who Billy is. So it sends it out to everybody. Billy gets it. Billy's like, oh, I'm Billy. This is my address. And then Billy sends it back so that way I know what Billy's address is going forward. That's a broadcast. That's an example of a broadcast. Okay. So routers by default won't forward any broadcasts. So when the broadcast goes out from me, it goes to the switch, and then it goes out to everybody from the switch. It goes out to everybody. When the router receives that broadcast, it's not going to send it over to our second network. It's not going to. It's going to look at that and be like, and throw it away. Routers use the logical address in a network layer header to determine the next hop router to forward the packet to. So routers are going to look at the IP address, the logical address, not the hardware address, the logical IP address in the header to determine the next hop router to forward the packet to. Remember, we have the source and our destination address in that header. And we'll talk about headers in a bit. Don't stress about that too much for now. Routers can use access lists created by an administrator to control security on the types of packets that are allowed to enter or exit an interface. Routers can provide layer 2 bridging functions if needed and can simultaneously route through the same interface. We'll cover bridging functions later. Layer 3 devices, routers in this case, provide connections between virtual LANs. I said that weird. Provide connection between virtual LANs or VLANs. We'll talk about VLANs a lot later. Don't worry about it too much. I can just give you guys a brief explanation. Just for funsies. So VLAN, right? I'm going to go back to my router. So when I want to create a VLAN, so we can think about the idea that all of my stuff in my house is going to be assigned an IP address by my router right here. And what I can do is I can isolate each of these things where they can't talk to each other. For example, if I have a smart TV, which I do, so this cable here goes to my wireless access point, which is this box down here. So this does all of my Wi-Fi. I have everything set up in my house to where anything connected to my Wi-Fi cannot talk to my computer. And that's a virtual LAN, virtual local area network. So I have it set up where They are completely separate networks and they should never talk to each other. So when anything like my smart TVs or my tablet or my cell phone does a broadcast to kind of figure out what's going on. For example, if I pull up my phone and I want to do a smart connection to my TV, right? So I get on my phone and I go into Smart View. Is that what it's called? Yeah, I go into Smart View. So that way I can get my phone pulled up on my TV. My phone is going to send data to my wireless access point, and it's going to do a broadcast to try to figure out what TV is where. And then the TV will respond back. However, I have it set up to where when I do a broadcast, none of the data ever goes back to the router and then to my computer because I've created what's called a virtual LAN or a VLAN, virtual local area network. But we'll definitely talk about that way later on. So nothing to stress out for now. Switch back. All right. Let's see. Routers. Yes. Um, provide connection can provide connection between virtual LANs. Routers can provide quality of service for specific types of network traffic. Yeah, so that's an interesting thing. I have my router programmed as well to where it's like anything coming from my computer gets all of the resources. My computer can hog up everything as much as it wants and as much as it can use, and it will lower the amount of connectivity my other devices have in order to ensure that my computer gets everything at once. All right. And that finishes up layer 3 routers. So let's refresh everything. All right. So layer 3 routers transports traffic between devices that aren't locally attached. Looks at IP addresses. Uses data packets. The protocols involved are IP, Internet Protocol, such as IPv4 and IPv6. It also sends route updates, which is just a way for routers to learn about other networks, other routers it's attached to. Learn about your neighbors. Okay. So next is the data link layer. But before we hop into that, I'm going to take a quick break. I'll be back in less than a minute. So give me just a second. All right, I'm back. Time to refresh the coffee. have a copy. Yeah, I think overall, being new to the IT field, and this is my very first core class. I studied a little bit of the Coursera IT support fundamentals, and then I started studying the CompTIA A plus a little bit, and then I started this class, and oh my goodness, like the information overload was kind of wild. So yeah, I think it's super awesome though. And then going back and doing this with you guys is so good for me. It really is. It really reinforces the concepts and the knowledge. Like, I love it. We're almost done though. We're almost done with chapter 2. We're almost done. Like, we're about 2/3 of the way. So the next one, the next layer is the data link layer. Things get a little bit more complex here. So let's get our notebook out. We have data link. Okay. So data link, and we'll get our notes back up before I forget. That'll be embarrassing. All I did was add data link here, which is layer 2. All right. The data link layer, it provides the physical transmission of data and handles error notification, network topology, and flow control. This means the data link layer ensures that messages are delivered to the proper device on a LAN using the hardware MAC address. Hardware MAC address. So MAC address, MAC, is media access control. All right, MAC address. And we're gonna just put that note here right now. So we have IP addresses, for layer 3, and then we have MAC address for layer 2. All right. MAC address, hardware address, IP address, logical address, MAC address, hardware address, the burnt in address. Yes. So this means that the data link layer ensures that messages are delivered to the proper device on a LAN using hardware MAC addresses and translate messages from the network layer into bits for the physical layer to transmit. All right, we're going to go over that one more time. I'm going to read that one more time. The data link layer uses the hardware MAC address and translate messages from the network layer into bits for the physical layer to transmit. Okay? The data link layer formats the message into pieces. Each of those pieces are called a frame. Remember, network, we had packets. Data link layer is frame. Data link layer is frame. So, network layer, we had packets. In this layer, we have frames. All right, that is something worth really dedicating to memory. We have packets, and then we have frames. Frames are with the hardware address, the data link layer. Network layer uses routers, IP addresses, and sends packets. Data link layer uses hardware address and uses frames. Frames are then sent to the physical layer as ones and zeros, which is binary, ones and zeros. Okay, one more time, just going to reread that because it's worth emphasizing. All right. The layer 2 data link layer ensures messages are delivered to the proper device on a LAN using the hardware MAC addresses and translates messages from the network layer into bits for the physical layer to transmit. The data link layer formats messages into pieces, each called a frame, and adds a customized header containing the destination and source hardware addresses. This added information forms a sort of capsule that surrounds the original message in much the same way that engines, navigational devices, and other tools were attached to the lunar module. We can skip past that. The big thing here, and just to give a very basic illustration, is when we come from the router, so we have a router with our packet. That's supposed to be a P. With our packet. When we go down to the data link layer, what we're talking about is we take the packet, we take a packet, and then we add information to it. So this is the information we add to it, and that's what we're talking about with encapsulation. Okay? So we have a packet, and then at the data link layer, it's encapsulated. Okay? It's encapsulated. We have data that's put at the front and put at the back of it. That's all encapsulation means. It's surrounded. There we go. Okay. So the data link layer formats messages into pieces called frames and adds a customized header containing the destination and source hardware MAC address. This added information forms a sort of capsule that surrounds the original message. The various pieces of equipment we can skip past that. Yeah, he thinks it's a great analogy. I don't know. It doesn't work for my brain. It's important for you to understand that routers, which work on the network layer, don't care about where a particular host is located. So they don't care about hardware addresses. That's what that means. They're only concerned about where networks are located and the best way to reach them, including remote ones. I'm going to skip past some of this stuff. The data link layer is responsible for the unique identification of each device that resides on a local network. For a host to send packets to individual hosts on a local network, as well as transmit packets between routers, the data link layer uses hardware addressing. Each time a packet is sent between routers, it's framed with control information at the data link layer. However, that information is stripped off at the receiving router, and only the original packet is left completely intact. This framing of the packet continues for each hop until the packet is finally delivered to the correct receiving host. It's important to understand that the packet itself is never altered along the route. It's only encapsulated with the type of control information required for it to properly pass on to the different media types. All right. So they provide an image here that we can reference real quick. This image right here shows the data link layer with the Ethernet and the IEEE specifications. We can write in what IEEE is here. It's the Institute. Well, let's write in IEEE, which is the Institute of Electrical and Electronics Engineers. So essentially speaking, the IEEE, the Institute of Electrical and Electronics Engineers, this was a group of people that put in a lot of the work that went into creating the standards in which devices can communicate. And yeah, so I think we're going to go over logical link control and media access control in a little bit. And then these 802.5, 802.3, 802.2, those are just different standards that are put into place. So yeah, you see down here, we're going to go over those in just a second. So when you check out and notice the IEEE 802.2 standards, it's not only used in conjunction with the other IEEE standards, it also adds functionality to those standards. The IEEE data link layer has two sublayers, which are media access control, which we've identified over here, right? Our MAC address. And then our logical link control, which is LLC. So let's cut that, and then we'll put those together. And then we have LLC, which is logical link control. So media access control defines how packets are placed on the media. Contention media access is first come, first served. Access where everyone shares the same bandwidth. Hence the name physical addressing is defined here. As are logical topologies. Logical topology, it's the signal path through a physical topology. Line discipline, error notifications, not correction, ordered delivery of frames, and optional flow controls can be used at this sublayer. So let's go back over that real quick. So media access control defines how packets are placed on the media. Contention media access is first come, first served access, where everybody shares the same bandwidth. Hence the name. So I think contention media access is its own thing. Let's look into that real quick, because I'm not an expert and it would be good to look into. So let's see. What is contention media access? A network communication method where multiple devices compete for access to a shared medium, such as a wire or radio frequency to transmit data. So, okay. Yeah, I'm trying to figure out though the reason why in the study guide they would put contention media access in there as first come first serve. Like I understand that with media access control, physical addressing is defined here, as are logical topologies. That makes sense. Logical topology is just the physical topology of the network, like where the wires are and the way in which data goes through those wires. I'm sorry, yeah, that's physical topology. Logical topologies here are the specific paths in which data travels. So the difference is, if we're going on to explain logical versus physical topology, So physical topology is this entire thing. It's all of the computers, all of the routers, all of the servers, all of the wires, every single thing here. Logical topology is how my data will go from this computer to this computer. It will go through this wire into this switch. It'll go from this switch into this wire. It will go into this router through this wire, into this router, then through this wire, into this router, to this wire, to this switch, through the wire, into the computer. So that's the difference between logical and physical topology. Physical topology is this entire thing, where all of the wires, where all the computers, where everything is located. Logical topology is how data goes from a device through the network to another device. Okay, so going back to it, contention media access is first come, first served access where everybody shares the same bandwidth. That's okay. And then logical topology is the signal path through a physical topology. Line discipline, error notification, not correction, order delivery of frames, and optional flow controls can also be used at this sublayer. So media access control, we'll go ahead and put here. So helps to write. Media access control defines how packets are placed on the media. How packets are placed on the media. And media here is just a term that's being used to define like our wires and stuff. But I also noted that specifically in the study guide, they outlined that it's packets that are placed on the media instead of frames. So I don't know if that was just an error or not. So next thing. Oh, okay. Another thing to note here. Not too sure about line discipline error notification. So we'll look into that in just a second. So we'll just go ahead and put that down, that line discipline error notification. Not correction. Ordered delivery of frames. Ordered delivery of frames. And optional. Hey, welcome back. Welcome back. Hey, Chris loves tofu. So I'm using the Remarkable Paper Pro 2. That's what I'm using. Let's see. And optional flow controls can be used at this sublayer. Optional flow controls. Yeah, so over here, yeah, this is the Remarkable Paper Pro, and I'll show that to you real quick. That's it's pretty snazzy, and yeah, you can link it up to your computer, your phone, and all sorts of other things. And I love it because there's no bloatware, if you would, on this thing at all. There's no ads, there's no nothing. It takes notes perfectly, and yeah, I love this thing a lot. They are a little pricey though. They're about $650, but it's the Remarkable Paper Pro 2. Put that in the comments. just in case. But yeah, it doesn't cost a monthly subscription or anything like that either, unless you want the other templates, but I don't think you need it at all. But worth checking out at Best Buy, but they are a little spendy. Okay, logical link control. Responsible for identifying network layer protocols and then encapsulating them. An LLC header tells the data link layer what to do with a packet once the frame is received. It works like this. A host receives a frame and looks in the LLC header to find out where the packet is destined. Say the IP protocol at the network layer, the LLC, which is the logical link control, can also provide flow controls and sequencing of control bits. Yeah, it is pretty nice. Like you can do the whole wireless sharing of the screen. I definitely like it a lot. It's pretty awesome, and it just feels good to write on. I like it a lot. And you can do a bunch of stuff here. You can change the pen type that you use, the color of what you use. You can highlight things, and then you can also pull your books into this as well. Like if you download it onto your computer, you can just drag and drop PDFs in there. And you're able to read those pretty effectively, and it works a lot like a Kindle in that sense. So going back and recapping the logical link control. Logical link control. So it identifies the network layer protocols and then encapsulates them. So encapsulates network layer protocols. All right. Then it tells the data link layer what to do with the packet once a frame is received. So when a frame is received, data link, what to do, packet. And then the logical link control is responsible for identifying where a packet is destined. And he goes on to explain that, like the IP protocol at the network layer, for example, can also provide flow control and sequencing of control bits. All right. I appreciate it. I appreciate it, man. So Project 802. So the 802 standards are something that was put in place by the IEEE, which is the Institute of Electrical and Electronics Engineers. He goes on to explain that one of the major components of the data link layer is the result of the IEEE's 802 subcommittees and their work on the standards for local area and metropolitan area networks. Metropolitan area networks were our MANs, our MANs. So we can go ahead and make a note of that. MAN, which is our metropolitan. Of course, I'd spell that wrong. Area network. And then, of course, we have our LAN, which is our local area network. And then they give some history on it, meeting in February 1980. And they used the 80 from 1980 and the 2 from the second month to create the name Project 802. Yeah. And then they go over a different list of all of the standards that are put in place. And I don't think at this point we need to really focus on committing all of these to memory yet. We go over a lot of these things in later chapters, the different 802 standards. And we're going on to our last little bit here, which is the physical layer, last but not least. So to recap at the data link layer, we have MAC addresses and we utilize frames. Oh, I went over to big camera and I didn't go back to my desktop. I apologize. So we have our data link layer and we have frames. We have our MAC address. MAC stands for Media Access Control. And then LLC is written in here, which is our logical link controls. So the media access control defines how packets are placed on the media. There are different aspects to that, such as line discipline, error notification, not error correction, ordered delivery of frames, and optional flow controls. So we were going to look into line discipline because that's something I'm not super familiar with. Like I've heard the term, but I've not seen what it actually is. What is line discipline in media access control? So line discipline in media access control is a data link layer function that coordinates communication between devices on a shared network to prevent collisions, determining which device is allowed to transmit data and when. It ensures that before data is sent, the receiver is ready to accept it, thereby managing the connection and organizing the flow of data, particularly in half-duplex systems. Now remember, half-duplex is when only one device can communicate at a time. We gave that analogy of, imagine you have a 2-lane road, but there's construction being done, and you have the guys at either side with the stop signs that can flip around. So transmission can only happen or receiving can only happen, but we can't do both at the same time. Both at the same time is full duplex. All right, key aspects of line discipline is coordination. It establishes communication continuity between sender and receiver, ensuring only one device transmits at a time in half-duplex links, or that the primary station manages access. Collision prevention, it prevents collision by organizing how multiple nodes access the shared medium. Receiver readiness, it confirms the existence and readiness of the receiver before transmitting data. Let's see. Primary methods of line discipline is ENQ/acknowledgement, which is inquiry and acknowledgement. It uses peer-to-peer or dedicated links. The sender sends an inquiry frame to check if the receiver is ready. If the receiver replies with a positive ACK, the transmission proceeds. If negative, acknowledgement, NAC, is sent, sender waits. Yeah, so that explains a little bit on line discipline around there. Okay, so once again, the recap, data link layer, layer 2, MAC address, frames. We have media access control. It defines how packets are placed on the media using line discipline, error notification, ordered delivery of frames, and optional flow controls. We have logical link control, which encapsulates network layer protocols. When a frame is received, it tells the data link what to do with the packet. All right, moving on to the physical layer, unless there's any questions. So with the physical layer, finally hitting the bottom. Well, not in a bad way. The physical layer does two important things. It sends and receives bits. Bits come only in values of 1 or 0. Side note, not to make things overly complicated, but quantum computing and quantum networking, if we're talking about that, it kind of changes things a little bit in that we can send ones, zeros, and we have a third option of 1 and 0. So, yeah, side note. So, bits only come in values of 1 or 0, a Morse code with numerical values. The physical layer communicates directly with the various types of actual communication media, which are our fiber, our Wi-Fi being radio signals, or our Ethernet via electrical signals. The physical layer communicates directly with the various types of actual communication media. Different kinds of media represent these bit values in different ways. Some use audio tones, and others employ state transitions, changes in voltage from high to low and low to high. Specific protocols are needed for each type of media to describe the proper bit pattern to be used, how data is encoded into the media signal, and various qualities of the physical media's attached interface. So as we kind of talked about earlier, when we have that three-way handshake, that's where we come up with synchronizing our clocks and setting up the rules. And after that, once we've synchronized and set up the rules, now we have, essentially speaking, a way for us to transmit the bits back and forth. And the physical layer is physically doing that. That's when we're physically transmitting the bits back and forth. The physical layer specifies the electrical, mechanical, procedural, and functional requirements for activating, maintaining, and deactivating a physical link between end systems. This layer is also where you identify the interface between the data terminal equipment, DTE, data terminal equipment. So DTE is data terminal equipment. And then the DCE, which is data communication equipment. Some older phone companies still call DCE data circuit terminating services, data circuit terminating equipment. The DCE is usually located at the customer, where the DTE, the data terminal equipment, is the actual device. The services attached to the DTE are most often accessed via the DCE device, which is a modem or channel service unit slash data service unit. So we have CSU, which is our channel service unit, and then we have the DSU. What I press? Which is our data service. I can spell today. Unit. Okay, let's backtrack through that. There was a lot of stuff to write down there. So the physical layer specifies the electrical, mechanical, procedural, and functional requirements for activating, maintaining, and deactivating a physical link between end systems. This layer is also where you identify the interface between the data terminal equipment and the data communication equipment. The data communication equipment is usually located at the customer, whereas the data terminal equipment is the attached device. The services available to the data terminal unit are most often accessed via the data communication equipment device, which is a modem or channel services unit slash data service unit. The physical layer's connection and different physical topologies are defined by the standards, allowing disparate systems to communicate. Finally, the physical layer specifies the layout of the transmission media, otherwise known as topology. A physical topology describes the way the cabling is physically laid out as opposed to the logical topology in the data link layer. The various physical topologies include bus, star, ring, and mesh that we talked about in the last chapter. Okay, so to summarize this, if we're going to, so for the physical layer, we have bits. All right, bits is our big thing with the physical layer. And then with the physical layer, we have our media, such as Ethernet, fiber, radio, and so on. It's how the data is actually physically transmitted from point A to point B. That's all we really need to take note at the physical layer, is how the data is transmitted from point A to point B. And then the physical layer also goes about talking about our topologies, our physical topology. All right, as we kind of showed with Cisco Packet Tracer. So if we pull that back up, and we talk about our physical topology here, that's where all of the computers, all of our switches, all of our Ethernet cables are all physically located. And remember, the logical topology compared to the physical topology is how a signal goes from any point to any other point. So if we gave an example of me trying to talk to John over here, our logical topology describes how the signal goes from me through the wire into the switch, from the switch through the wire into the router, router's exit interface through the wire to the router, router's exit interface through the wire to this router, exit interface to the switch through a wire, exit interface from the switch through a wire to this device. That's the logical topology. The physical topology is just how all of this is laid out. Okay. The next section is an introduction to encapsulation. Now let's go ahead and minimize this back down. So that is a rough breakdown of our 7 layers of the OSI model, which is our open systems interconnection model. All right. At the very top, we have our application layer, we have the presentation layer, we have the session layer. Those things are kind of grouped together. All right. They all kind of work together. And then after that, we break down into let's just scroll back up to the top so that way I can show. There we go. We have our transport layer, as we can see here. Let's get it to cooperate. There we go. We have our transport layer. Then we have our network layer, data link, and then finally physical. So application, presentation, and session, they're all kind of linked together, if you would. They kind of work around each other very closely. And then we have a distinct separation between our transport, network, data link, and physical layer. The top 3 define how applications between host machines communicate as well as end users. The bottom 4 define how data is transmitted from end to end. All right. Let's scroll back down before we go to encapsulation. So, intro to encapsulation. All right. So when a host transmits data across the network to another device, the data goes through encapsulation, where it's wrapped with protocol information at each layer of the OSI model, which is the Open Systems Interconnection model. Each layer communicates only with its peer layer on the receiving end device. To communicate and exchange information, each layer uses protocol data units, PDUs, protocol data units. And that's when we're talking about packets, frames, things of that nature. PDU is protocol data units, protocol data units. These hold the controller information attached to the data at each layer of the model. They're usually attached to the header in the front of the data field, but can also be in the trailer or end of it. At a transmitting device, the data encapsulation method works like this. The user information is converted to data for transmission on a network. Data is converted into segments, and a reliable connection is set up between the transmitting and receiving hosts. Segments are converted to packets or datagrams, and a logical address is placed in the header so each packet can be routed through an internetwork. A packet carries a segment of data. 4. Packets or datagrams are converted to frames for transmission on the local network. Hardware or Ethernet addresses are used to uniquely identify hosts on a local network segment. Frames carry packets. Frames are converted to bits, and a digital encoding and clocking scheme is used. All right. And then we have a really awesome figure that we can look at here, which we can kind of see, right? So when we're working on our application layer, that's the thing that we're interacting with. And then it goes down. We have our application, presentation, and session layer. We call that the upper layer data. And then that upper layer data goes down to the transport, and then it's called a segment. And then we can see how we have a header, which is our transmission control protocol. Header is attached to the front of it. All right. From there, it goes down to the network. All right, as a packet. So this whole thing right here is called a segment. This whole thing right here is called a segment. And then we can see that the segment is represented as this. So imagine that we have the TCP header, upper layer data, and then segment. Then as we get to the network layer, its name changes to packet. And a packet has a segment with an IP header. IP, Internet Protocol header. And then from there, it can travel to another network, or if we're going to be sending it from our routers are at the layer 3, down to the receiving end, the router is going to frame that with a MAC header or an LLC header, and then we have what's called a frame check sequence that's added to it. So all of this information is a packet. And our packet is here, and then as it comes down, it's turned into a frame when we add our LLC header and our MAC header, as well as a frame check sequence. And all a frame check sequence is, the FCS, is a computer goes and looks at all of the data there, and it does a lot of work with polynomials, and it does math, and it comes up with a numerical quantification for all of the data. And that helps to ensure that after we send the frame off, the receiving end can check the frame check sequence, and it does what's called a cyclic redundancy check on the frame to where it does the math too. It's called a CRC, and we'll get into that later, so it's nothing to stress out about too much. But it does a check on it, does the math, and it makes sure that the frame check sequence and its math line up. And it's like, okay, nothing's been messed up, good to go. And then from here, at the data link layer, it's turned into the bits, the ones and zeros. So that's how it all works. And then once it's into the ones and zeros, it's sent across our physical media, and then it's reconstructed up, assessed, and then if it needs to go through the process again, it's done again. So it seems like a lot to go from the top all the way down over to a different place and then build it back up, reassess it, then break it all back down and send it over again. And it's a very fluid motion as it does that. Okay. So that's essentially what encapsulation is. And if we're drawing a picture of it, again, we have our, we'll just call it data. We have our data. So let's just say, actually, no, let's just say I have a picture of a cat. Here's my cat. And I want to send you a picture of the cat. So the cat goes through the application presentation session layer, gets converted into a segment. And when we convert it into a segment, we're adding the TCP header. All right. And this right here is a segment. So that segment right here the segment works its way down, and we're at the transport layer. Our segment works its way down to the next layer, which is the network layer. And from here, we add our IP header. Okay. And then this whole thing here is a packet. This whole thing. And then from there, our packet moves down. And then we can either add the MAC header or the LLC header, depending. And then we also add our frame check sequence. From there, it's converted into ones and zeros. That's kind of what's being illustrated here. And that's what encapsulation is. You're just surrounding your data with other information. So modulation techniques. And yeah, we'll just keep this. And we'll move our way up. Get some clean space. Some modulation. All right. Time for a sip of coffee. So in networking, modulation is the process of varying one or more properties of a waveform called the carrier signal. With a signal that typically contains information to be transmitted. Modulation of a waveform transforms a baseband, Ethernet or wireless, messages into signals called a passband. A passband is known as a band-pass filtered signal. It's a range of frequencies or wavelengths that can pass through a filter without being attenuated. In current networks, modulation takes a digital or analog signal and puts it in another signal that can be physically transmitted. So, here's a way of thinking about this to make it a little bit more simplistic. And we'll go back over to my big camera. Camera wants to cooperate. So I have my router and everything here, right? And then we have a modem, which is a modulation demodulation machine. That's what it does. So it takes the digital signal. Boy, It takes the digital signal from my router. Router goes and connects to that via Ethernet, and it turns it into an analog signal with a waveform through the coaxial cable, and then from there, that transmission media, which is like the phone line that go all the way to my internet service provider. That's what modulation is. There's different forms of modulation though, because if you think about the idea of taking Ethernet cable and then maybe I'm converting it to fiber, which is taking electrical signals and converting it into photons. Or I take electrical signals and I convert it into radio frequency to send to satellites. That's what modulation is. Modulation is taking a signal and changing it into another type of signal that can be transmitted. Demodulation is taking that carrier signal. Carrier signal is what our ISP wants to use to transmit, whether that's fiber, and then reconverting it back to a digital signal. So that's what modulation is in essence. And you have a device called a modem that does that for you, modulates and demodulates. So when data comes via the coax cable into the modem, it demodulates it, puts it in a way that can be transmitted across the Ethernet cables. And then when I send data, like right now, I'm uploading data to YouTube, right? So it's going from my computer into the router, from the router into the modem, gets turned into a signal that can be transferred through the coax cable, the carrier signal. And from there goes all the way to my ISP. The ISP demodulates it, looks at all of the information, figures out where it has to go, modulates it back into carrier signal that can be then sent off toward a process repeat. All right. Gets it back here. A modulator is a device that performs modulation of a signal, and a demodulator is a device that performs demodulation, the inverse of modulation. We typically just call these modems, from modulator, demodulator, which can perform both operations. The purpose of a digital modulation is to transfer a digital bit stream over an analog base pass channel. A good example would be data transmitting over the public switch telephone network, where a bandpass filter limits the frequency range to 300 to 3400 hertz, or over a limited radio frequency band. The purpose of an analog modulation is to transfer an analog baseband or low pass signal, for example, an audio signal, wireless network, or TV signal, over an analog bandpass channel at different frequencies. Analog and digital modulation use something called frequency division multiplexing. And we'll put that in here because it's an acronym. So FDM is frequency division multiplexing, where several low-pass information signals are transferred simultaneously over the same shared physical network, using separate passband channels or several different types of frequencies. The digital baseband modulation method found in our Ethernet networks is also called the line coding, are used to transfer a digital bit stream over a baseband channel. Baseband means the signal being modulated used the complete available bandwidth. Okay, so let's break down some of these terms. All right. Working our way from the top down. So we have passband. We have passband or band pass. So passband or bandpass, which is also known as a filtered signal. So that's something we need to go and work on getting clarification on. Then we have attenuated. Be nice to have a definition on that. And perfect. So the purpose of an analog modulation is to transfer an analog baseband or low pass signal. Perfect. And then we had baseband, if I recall correctly. Baseband. All right, so some things that I personally want a little bit more clarification on, just because I skimmed through this the first time through, and I was like, it didn't seem like it was really worth super committing the effort into memorizing, but it's something we need to go about understanding a little bit better. And I do definitely think that a Google search and understanding these concepts before we dive super deep into them makes things a little bit better. So we'll go with band versus bass band. So band pass signals represent raw information, voice data at low frequencies near 0 Hz, suited for short distance, unmodulated transmission. Bandpass or passband signals are modulated to higher frequency, allowing long distance wireless transmission over specific bands. Baseband is typically base 0 Hz, while bandpass is centered around a carrier frequency. So let's see. Let's go to the bandpass because we're working on that. So the definition: a signal shifted in frequency to be centered around a high frequency carrier. Okay, so bandpass / passband is the unmodulated signal that needs, I can spell, to be modified for transmission. So the bandpass or passband, a signal shifted in frequency to be centered around a high frequency carrier. Spectrum occupies a specific range of frequencies higher than 0. Modulation, it's modulated, so AM, FM, QAM. Use case, long distance wireless radio cellular network. Let's see. Baseband. Let's move up to baseband. Definition: the original frequency range of the information signal. This one isn't really explaining it in a way that's making all the sense to me. So let's go back up. So baseband signal represents raw information. So that's our baseband. I got it backwards. See? Not perfect. Just a regular human. So baseband. Baseband is our unmodulated. So it's the raw information, voice data, low frequencies, suited for short distance. Unmodulated transmission. Band pass or passband signals are modulated to higher frequencies. So baseband is unmodulated, and we can think of it as unmodified. It's not modified. So yes, baseband is unmodified, whereas band pass or passband signals are changed to the carrier signal, which is at the higher frequency and can go longer distance. So we'll go band pass or passband are modified to higher frequencies for transmission. Perfect. So baseband, let's double check, make sure we're tracking this. The definition is the original frequency range of the information signal. For example, audio, baseband video. Spectrum is a range from near 0 hertz to a maximum cutoff frequency. It is unmodulated, and it's for short distance communication such as USB cables, Ethernet cables, or analog audio cables. So low power consumption, similar implementation, not suitable for antenna transmission. The band pass or passband signals, a signal shifted in frequency to be centered around a high frequency carrier. Spectrum occupies a specific range of frequencies higher than 0, for example, radio bands. Modulation, it is modulated, for example, AM, FM, QAM. Okay, so let's go back and tackle this again, work through it a little bit slower. In networks, modulation is a process of varying one or more properties of a waveform called the carrier signal. So the carrier signal is a signal that typically contains information to be transmitted. Called the carrier signal, with a signal that typically contains information to be transmitted. Modulation of a waveform transforms a baseband. So the baseband is our unmodulated signal, which is our Ethernet or wireless message signal, into a passband signal. Passband, also known as band pass filtered signal, is the range of frequencies or wavelengths that can pass through a filter without being attenuated. And attenuated, as far as I remember, means like if it goes through the filter, it's not going to lose anything. Okay, exactly. Attenuated means having been reduced in force, effect, or value. So let's go back and check that again. So a band pass filtered signal is the range of frequencies or wavelengths that can pass through a filter without being attenuated. In current networks, modulation takes a digital or analog signal and puts it in another signal that can be physically transmitted. So as I was saying, the modulator takes stuff from my Ethernet cable, converts it into something that could be sent long distance to the ISP or the internet service provider, and vice versa. It takes the signal coming from them and converts it in a way that my Ethernet cables can transfer it. All right. I think we're tracking. A modulator is a device that performs modulation of a signal, and a demodulator is a device that performs demodulation. Okay, perfect. The purpose of a digital modulation is to transfer a digital bit stream over an analog band pass channel. Analog band pass. All right, that makes sense to me. A good example would be data transferring over the public switched telephone network, where a band pass filter limits the frequency range to 300 to 3400 hertz, or over a limited radio frequency band. The purpose of an analog modulation is to transfer an analog baseband signal for example, an audio signal, wireless network, or TV signal over an analog band pass channel at a different frequency. All right. So yeah, this is all starting to track. In essence, what we're talking about is we take something that isn't suited for long distance transmission. We take our signal, we change it so that way it is suited for that long distance transmission. We send it out, and then if we receive stuff back, we just do the inverse. Perfect. The digital baseband modulation methods found in our Ethernet networks, and also known as line coding, are used to transfer a digital bit stream over a baseband channel. Baseband means that the signal is being modulated, the digital signal is being modulated used the complete available bandwidth. All right, so moving on from there, we have time division multiplexing. Time division multiplexing, or TDM, is a method of transmitting and receiving many independent signals over a common signal path by means of synchronized network devices at each end of the transmission line, so that each signal appears on the line only a fraction of time in an alternating path, and the receiving end demultiplexes the signal back to its original form. All right. So one thing that I am a little bit familiar with, and we'll test the theory on how accurate that is when we're talking about this. So if we're talking about sending a signal, give me a straight line, there we go. So if we're talking about a signal, what we're talking about with time division multiplexing is the ability to send multiple signals at the same time. Well, how do we do that? Well, what is a signal, right? Let's look at a signal. So we can imagine this is our signal. Well, we have the wavelength, which is peak to peak. That's our wavelength. And what we can do is we can have signals that have different wavelengths So you can see how the wavelength here is way different than our initial one. Actually, let me use different colors. That way it's easier to see. So we have our first wavelength, which I've marked in black. And then we can have a different wavelength, which I'll mark in blue. And then we can have another wavelength, which we can mark in red, which will be here. All right, so we have a really large wavelength, which is our first one. We have a shorter wavelength, and then we have an even shorter wavelength. And one thing we can do is, if we're keeping our eyes out for a specific wavelength, for a specific route of communication, the way we can adjust whether something represents a 1 or a 0 is we can adjust the amplitude. So what is the amplitude? So we have our x-axis right here. The amplitude is the distance from the x-axis. So maybe this represents a 1, and then this can be a 1. So any value from here, let's just say to here, can be a 1. And then we can represent this as a 0. So the wavelengths are the same. And let me get this back up. So we can have the wavelengths be the same, but we can have the amplitude here to here can represent 0, and then anything from here to here can represent 1. And that's how we can have different signals, and we can adjust the amplitude in order to have that represent either a 0 or a 1. And then have the same wavelength in order to represent our different signals. All right. So time division multiplexing is a method of transmitting and receiving many independent signals over a common signal path by means of synchronized network devices at each end of the transmission line, so that each signal appears on the line only a fraction of time in an alternating pattern. The receiving end demultiplexes, which is just a matter of splitting those signals apart, demultiplexes the signal back to its original form. After you've learned more foundational material about networking in the next few chapters, I'll come back to the encapsulation and discuss it further in Chapter 6. And then, in Chapter 6, we get into TCP/IP and a really in-depth breakdown of that. So, we're finished. We're finished with covering all the hard stuff. So we can get into the summary and then take our quiz together. So, summary. Let's see, we've covered a ton of foundational information. So we discussed internetworking model and the advantage of having them. We discussed the OSI model, the 7-layer model used to help application developers design applications that can run on any type of system or network. Each layer has its own specific job and select responsibilities within the model to ensure that solid, effective communications do occur. We also discussed a little bit about encapsulation, and then we finished with an introduction to modulation of a digital analog signal. So for the exam essentials, remember the OSI layers. We just have to really commit those 7 layers to memory, which is the application presentation session, then transport, network, data link, and physical layers. Know the sub-layers of the data link layer, which would be the LLC and MAC address. The LLC sublayer is responsible primarily for multiplexing of network layer protocols. And the MAC sublayer is responsible for physical addressing and determining the appropriate time to place data on the network. Knowing the devices that operate at each layer of the OSI model. Hubs and repeaters only see bits, so they're layer 1. Switches are layer 2. Routers are layer 3. All right. So written lab. Let's see if we can find the answers. Which layer chooses and determines the availability of communicating partners along with the resources necessary to make the connection? Coordinates partner applications and forms a consensus on procedures for controlling data integrity and error recovery. Well, what do you think? That would, to me, that would be the application layer. Which layer is responsible for converting frames from the data link layer into electrical signals? That would be the physical layer. Which layer is routing implemented, enabling connections and path selection between 2 end systems? That would be the layer 3. Layer 3, network layer. Which layer defines how data is formatted, presented, encoded, and converted? That would be the layer 6, presentation layer. I don't have the answers here. So Yeah, there's no answers. I'm just showing. Okay. Which layer manages the transmission of data across the physical link and is primarily concerned with physical addressing and the ordered delivery of frames? I'm thinking that's the layer 2 data link layer. Which layer is used for reliable communication between end nodes over the network and provides mechanisms for establishing, maintaining, and terminating virtual circuits as well as controlling the flow of information? Thinking that's the layer 5 session layer. Which layer provides logical addressing that routers use for path determination? I'm thinking that would be the layer 3 network layer. Which layer specifies voltage, wire speeds, and connector pinouts and moves bits between devices? That would be the layer 1 physical. And which layer combines bits into bytes and bytes into frames and uses MAC addressing? That'd be the layer 2 data link layer. I'm thinking those are the right answers. We'll go back and check here in a second. All right, review questions. Host 1 sends a SYN packet to host 2. What will host 2 send in response? The answers are A, ACK, B, NAC, C, SYN ACK, D, SYN NAC, or E, SYN. So the answer is C, SYN ACK, SYN ACK. That's the second step in setting up a virtual circuit. TCP and UDP reside at which layer of the OSI model? A1, B2, C3, D4. Well, layer 1 is physical, layer 2 is the data link, layer 3 is the network layer, and layer 4 is the transport layer. So I would say that would be layer 4, the transport layer. Which layer of the OSI model, what's OSI stand for? Open Systems Interconnection. Which layer of the OSI model is responsible for, oh, wait, there we go. Sorry, I was reading the wrong one. Question 3. Which layer of the OSI model provides an entry point for programs to access the network infrastructure? A, application, B, transport, C, network, or D, physical? Which layer of the OSI model provides an entry point for programs to access the network infrastructure? So specifically with accessing the network infrastructure, that's a good one. My gut tells me that it's the transport layer, which would be B. We'll see if I'm wrong. I'm probably wrong there. You are connected to a server on the internet, and you click a link on the server and receive a timeout message. What layer could be the source of this message? A, application, B, transport, C, network, or D, physical? Let's see. I'm thinking it's going to be the transport layer, considering that the transport layer is what's going to create the virtual circuit. And then in addition to that, when they're establishing the rules, it sets a time for how much time is allowed between waiting on the system to send a response or not. So yeah, I'm going to go with transport for 4B. And once again, we'll check the answers. I'm probably wrong, and that's okay if I'm wrong. Let's see, number 5. Which layer of the OSI model is responsible for code and character set conversion as well as reorganizing data formats? A, application, B, presentation, C, session, D, network. Which layer of the OSI model is responsible for code and character set conversion as well as reorganizing data formats? I'm going to go with B, presentation layer. We'll see if I'm right about that. It's either presentation or session. All right. At which layer of the OSI model do bridges, hubs, and routers primarily operate respectively? So bridges, hubs, and routers. Bridges, hubs, and routers. So let's see. Got to draw it back on. Like hubs are easy. That's the physical layer. Routers are easy. That's the network layer. I got to remember bridges. I think bridges do look at the MAC address would be the layer 2 or data link. So data link, physical, then network, which is C. C, data link, physical, network. All right, 7. Which layer of the OSI model is responsible for converting data into signals appropriate for transmission media? Well, that's where we're going to be modulating. And I think that'll be D, the physical. 8. A receiving host has failed to receive all segments that should be acknowledged. What can the host do to improve the reliability of this communication session? A, send a different source port number. B, restart the virtual circuit. C, decrease the sequence number. Or D, decrease the window size. A receiving host has failed to receive all segments that should be acknowledged. What can the host do to improve the reliability of the communication session? So I'm going to go with D, decrease the window size, because like if we're sending windows that are too big, sending too many pieces over and it's exceeding the buffers of the receiving device, if we decrease the window size and give it more time to process smaller batches of data, I think that would probably be better. What layer 1 device can be used to enlarge the area covered by a single LAN segment? So layer 1 is specified there. The answer is firewall, NIC, hub, repeater, or RJ45. Oh, and we can choose 2. So firewall, no, that's not it. Network interface card, that's what plugs into the back of your computer. That allows your computer to send and receive data through Ethernet, or wireless or fiber, whatever. Hub, yeah, absolutely. The dumb hub. Hubs can send and receive data across a LAN. Repeater, yeah, absolutely. Repeaters do kind of the same thing as hubs. And then RJ45 transceiver, I don't think that's one of them. So I'm going to go with C and D, which is hub and repeater. Segmentation of data streams happen at which layer of the OSI model? Segmentation of data streams happen at which layer of the OSI model? Physical, data link, network, or transport? Physical, data link, network, or transport? I'm thinking transport. We'll see if I'm right. When data is well, like my initial go-to answer at that point would actually be, I think it was presentation. Presentation was, we could reference our notes, but I don't want to cheat. This is a test. But I'll go with transport. When data is encapsulated, which is the correct order? A, data, frame, packet, segment, bits. B, segment, data, packet frame bits. C, data segment packet frame bits. D, data segment frame packet bits. All right. So let's see. Let's think back. So we have our data. Our data gets encapsulated initially with the, what is it, the IP header. And that turns it into a segment. Segment gets encapsulated with TCP header and gets turned into a packet. That's at the network layer. The packet gets turned into a frame, and then from the frame it gets turned into bits. So I'm going to go with C, which is data segment packet frame bits. What are two purposes of segmentation with a bridge? Choose two. Let's see. A is to add more broadcast domains. Well, we don't want that. B is to create more collision domains. We don't want that either. C is to add more bandwidth for users, and D is to allow more broadcasts for users. Oh wait, actually we do want more broadcast domains, because more broadcasts and more collision domains allow for less to happen on that segment. So yeah. Also been going at this for quite some time now, 5 hours. So brain's getting a little foggy, if you would. Let's see. So I think we want to add more. Let's see. We covered more on routers. Bridges can operate at layer 2, which will add more broadcast domains and more collision domains, I believe. Well, we're still going to have more broadcasts at layer 2 devices. We'll just go with A and B for fun. Acknowledgements, sequencing, and flow controls are characteristics of which OSI layer? Layer 2, layer 3, layer 4, layer 7. Acknowledgements, sequencing, and flow controls. I'm going to go with layer 4, which would be our transport layer. 14. Which of the following is true regarding sequencing and acknowledgements? Choose all that apply. Sequencing and acknowledgements. The segments delivered are acknowledged back to the sender upon their receipt. Well, it depends on the window size, but yeah, sure. B. If a segment is not received, the virtual circuit must be restarted from the beginning at a slower transmission interval. That is not correct. C. Any segments not acknowledged are retransmitted. That is correct. So A and C so far. D. Segments are sequenced back into their proper order upon arrival at their destination. That is true. So A, B, and D. Oh, sorry, A, C, and D. And then E. All segments are retransmitted on time slot intervals. I think that's correct. If the time expires after they are transmitted, then they are retransmitted. So A, C, D, and E. What is the purpose of flow control? Oh, I kind of know this one off the top of my head. So let's see if I'm kind of right. I think the purpose of flow control is to prevent us from exceeding the buffers of the receiving device. So let's see. A is to ensure that data is retransmitted if an acknowledgement is not received. Yeah, that's true, I suppose. B is to reassemble segments in the correct order at the destination device. No, not really. C is to provide a means for the receiver to govern the amount of data sent by the sender. Yeah. And D is to regulate the size of each segment. No, that's not true. Let's go with C, to provide a means for the receiver to govern the amount of data being sent by the sender. 16. At which layer of the OSI model would you find IP? Well, that's going to be at the network layer, which is B. Of the following, which is the highest layer in the OSI model? we have transport, session, network, presentation. Well, starting from the bottom, we have physical, data link, network, transport, session, presentation, application. So that would be D, presentation. All right, just 3 more questions. Routers perform routing at which OSI layer? We have physical, data link, network, transport, application. I'm going to choose C, network. Which of the following mnemonic devices can you use to remember the first letter of each name of each layer of the OSI model in proper order? All people seem to need processed data. Always should people never threaten dog police? What? Please do not throw sausage pizza away. All people should try new professions. I guess please do not throw sausage pizza away. Which IEEE standard specifies the protocol for CSMA/CD? That was my bad for skipping over that, essentially speaking. So let's go back and we can just check that out real quick. So here's the project 802 and carrier sense. I can't remember the rest of that. Carrier sense, multi-point something collision domain is 802.3. So yeah, that'd be 802.3, which would be B. All right. Now I need to go about getting the answers to our question, which I'm going to move over here and log into my school real quick. So I'll be right back. We're just about there. Gotta remember. Okay, so Appendix A is answers to the written labs. Okay. We have one, which layer chooses and determines the availability of communicating partners along with the resources necessary to make the connection, coordinate partnering applications, and forms a consensus on procedures for controlling data integrity and error recovery. The answer was the application layer is responsible for finding the network resources broadcast from a server to adding flow controls and error control. 2, which layer is responsible for converting frames from the data link layer into electrical signals? The answer was the physical layer. 3, which layer is routing implemented, enabling connections and path selections between 2 end systems? The answer was the network layer. Provides routing through inter-network and logical addressing. 4, which layer defines how data is formatted, presented, encoded, and converted? The answer was presentation layer. 5, which layer is responsible for creating, managing, and terminating sessions between applications? The session layer sets up, maintains, and terminates sessions between applications. 6. Which layer manages the transmission of data across a physical link and is primarily concerned with physical addressing and the order delivery of frames. Protocol data units at the data link layer are called frames. And as you see the word frame and or the term physical addressing in your question, you know the answer is always data link layer. Okay, I like it. 7. Which layer is used for reliable communication between end nodes over the network and provides mechanisms for establishing, maintaining, and terminating virtual circuits as well as controlling the flow of information? The answer is the transport layer uses virtual circuits to create a reliable connection between two hosts. 8. Which layer provides logical addressing that routers use for path determination? Let me go back over to my desktop. That way we can work on this together. The answer is the network layer provides logical addressing, IP and or IPv6 addressing and routing. 9. Which layer specifies voltage, wire speed, and connector pin outs and moves bits between devices? That would be the physical layer. And 10. Which layer combines bits into bytes and bytes into frames when using and uses MAC addressing? And that's the data link layer. So, review questions. 1. A host sends a SYN packet to host 2. What will host 2 send in response? Let me go to Appendix B. Chapter 2. I'm in the wrong spot, I believe. There we go. There's Chapter 1. Here's Chapter 2. Okay, sweet. So the answer was C, the SYN-ACK. 2. TCP and UDP reside at which layer of the OSI model? I think I went with 4. And yes, TCP and UDP are transport layer protocols. The transport layer is layer 4 in the OSI model. So 3. Which layer of the OSI model provides an entry point for programs to access the network infrastructure? Which one did I go with? I think I went with B, right? So 3 is A. I was incorrect. A, the top layer of the OSI model gives applications access to the services that allow network access. 4, you are connected to a server on the internet and you click a link on the server and receive a timeout message. What layer could be the source of the message? I think I went with transport, didn't I? I think I did. And the answer is wrong for me. A. If the remote server is busy and does not respond to your web browser request, this is an application layer problem. All right. 5. Which layer of the OSI model is responsible for code and character set conversion as well as reorganizing data formats? Which one did I go with? I went with presentation, didn't I? And the answer is the presentation layer makes data presentable, quote unquote, for the application layer. 6. At which layers of the OSI model do bridges, hubs, and routers primarily operate respectively? I went with data link physical network, bridges, data link, hubs, physical routers network, data link physical network. So C, and the answer is C. Bridges like switches are at the data link layer. Hubs like repeaters are physical layer. Routers are network layer. 7. Which layer of the OSI model is responsible for converting data into signals appropriate for the transmission medium? I went through physical, I believe it was. And the answer is D. Physical layer's job is to convert data into impulses that are designed for wired or wireless medium being used on the attached segment. 8. A receiving host has failed to receive all segments that should be acknowledged. What can the host do to improve the reliability of this communication session? I think I went with D, decrease the window size. The answer is D. A receiving host can control the transmitter by using flow control. TCP uses windowing by default. By decreasing the window size, the receiving host can slow down the transmitting host so the receiving host does not overflow its buffers. All right. 9. Which layer 1 devices can be used to enlarge the area covered by a single LAN segment? I went with hubs and I believe it was repeaters, C and D. The answer is C and D. Not that you really want to enlarge a single collision domain, but hubs, multi-point repeaters, will provide this functionality for you. 10. Segmentation of the data stream happens at which layer of the OSI model? What did I choose? I think I went with transport. And the answer is D. The transport layer receives large data streams from the upper layers and breaks them up into smaller pieces called segments. 11. When data is encapsulated, what is the correct order? What did I go with? I went with data segment packet frame bits. Yeah, C. 11 is C. Yep, data segment packet frame bits. 12. What are two purposes for segmentation with a bridge? Choose two. I can just tell you I got this wrong. It is to create more collision domains, and C, to add more bandwidth for users. So B and C, bridges and switches break up collision domains, which allow more bandwidth for users. 13. Acknowledgements, sequencing, and flow controls are characteristics of which OSI layer? I think I went with 4. Layer 4. C. 13 is C. A reliable transport layer connection uses acknowledgements to make sure all data is received reliably. A reliable connection is defined by the use of acknowledgements, sequencing, and flow controls, which is characteristics of the transport layer, layer 4. 14. Which of the following is true regarding sequencing and acknowledgements? Choose all that apply. A, the segments delivered are acknowledged back to the sender upon receipt. Let's see. Let's just mark it down. So I definitely think A is something. B, if a segment is not received, the virtual circuit must be restarted. No, so not B. And then C, any segments not acknowledged or resent. Yeah, that's true. Segments are sequenced back into their proper order upon arrival at their destination. Yeah, that's right. And then E, all segments are retransmitted on time slot intervals. Let me specify my answer. I don't know if this is true or not, like if E is, but I think for E, all segments are retransmitted on time slot intervals. My perception is if there's a timeout, like I go to send something and then I wait and I haven't gotten acknowledged back, then I resend it. But I don't think that I send it, wait a little bit, and if I got something back, then I resend it again. So I think it's E as well, but depending. And 14, the answer is A, C, and D. So not E. So A, C, and D. When sequencing and acknowledgements are used, the segments delivered are acknowledged back to the sender upon their reception. At this point, any segments not acknowledged are retransmitted, and segments are sequenced back into proper order upon arrival at their destination. All right. So 15. What is the purpose of flow control? What did I go with? To ensure that data is retransmitted, if not acknowledged, if an acknowledgement is not received. No. To reassemble no. To provide a means for the yes. C. And yeah, I mean, I guess D. No, that's not true. So C. Yeah, 15 is C. Flow controls allow the receiving device to control the pace of the transmitting device so the receiving device's buffer does not overflow. At which layer of the OSMI model would you find IP? Networking. Yes, 16 is B. IP is a network layer protocol. TCP is an example of a transport layer protocol. Ethernet is an example of a data link layer protocol. And T1 can be considered a physical layer protocol. 17. Of the following, which is the highest layer of the OSI model? I went with presentation. And the answer is presentation is the 6th layer of the model. Only the application layer is higher. Routers perform routing at which OSI layer? And that was network. And the answer is C, network. A router is specified at the network layer, and a router routes packets. Routers can also be called layer 3 switches. 19. I went with please do not throw away sausage pizza. That's the answer. Yeah, the answer is C. The phrase please do not throw away sausage pizza contains the first letters of all the layers in order from layer 1 through 7. All people seem to need data processing works from the top down. The other options all have the right letters, just not the right order. Oh, I didn't look into that. And then 20 is B, which is 802.3. All right, everybody. I think that's about a wrap. I think that's a wrap for today. Yeah. Any questions before I head out? Is there anybody else in here still? Nope, just me again. All right, perfect. All right, let's go back to my big camera. All right, everybody. I wonder if everybody likes this. I've only had one person interacting with the stream. Thank you so much. Chris loves tofu. Appreciate you being here and your interaction. I enjoy doing this. It's a good teach back opportunity for me. As you see, I'm just a normal human. I don't claim to know all of the answers. I don't think I'm an expert by any, but yeah, it's fun working through this together. See you in the next one. I plan on doing this every Monday at 1900 hours Pacific Standard Time. Please feel free to join the next one. Have a good night.